morning, everyone. A very warm welcome to all of you, those present here in person and those joining us via the online stream.
It is with great pleasure and honor that we welcome you to the National Training Workshop on Weather Radar, Theory, Calibration, Maintenance, Data Analysis and Applications, NT Radar 2025, organized by Indian Institute of Tropical Meteorology, Pune.
As we commence this academic journey, it is our honor to who have graced this inaugural session. Honorable Secretary, Ministry of Earth Sciences, Dr. Mrityunjay Mahapatra, Director General, India Meteorological Department IMD, and Dr. V.S. Prasad, Director National Center for Medium Range Weather Forecasting. We welcome you, sir.
We invite Dr. A. Suryachandra Rao, Director IITM, to kindly join us on the stage.
We welcome Professor V. Chandrasekhar, Colorado State University, to the dais.
We may also invite Dr. G. Panditurai, Project Director of the Atmospheric Research Testbeds, to take his place on the stage.
We cordially request Dr. Subrata Kumar Das, convener of this workshop, to join the dignitaries. Uh,
Teams.
they've done. As a gesture of appreciation, we would now like to felicitate our distinguished dignitaries. We request Dr. A. Surachandra Rao, Director IITM, to kindly felicitate Professor V. Chandrasekhar from CSU.
H. Suryachandra Rao, Director IITM. We now request Dr. Subrata Kumar Das to felicitate Dr. G. Panditurai, Project Director, ART.
Dr. Mahapatra, DGMP, Dr. V.S. Prasad, Head NCMA WF, Professor Chandrasekhar, who is on our dais, Pandi and Subrata, and distinguished guests from Italy and other participants from different IMD and other institutes. A very good morning to all of you and a warm welcome to today's event, National Training Workshop on Weather Radars. As you all know, IITM is a unique institute. Here, what we do is we cover each and every aspect of meteorology, particularly we cover each and every aspect of meteorology, particularly tropical meteorology. Either it is observational, state-of-the-art observations, or state-of-the-art models, dynamical models, or the emerging technologies, anything you name it, you have it in IITM. So that way it is very unique institution where we carry out research from observations, modeling, emerging technologies, everything. So at IITM, we use all the tools that are available to any researcher in the world. So you name it, you have it them here. So as a institution, we are all proud of that we get all these facilities that are available to all our scientists at any given time. Regarding today's training workshop, we have been at the forefront of atmospheric research and are deeply committed to advancing radar, meteorology, and observational science. As you all know, that weather radars have been indispensable tools in modern meteorology research, particularly in the study of Indian monsoon. Given the complexity of monsoon dynamics, you know that predicting monsoon is the toughest challenge. As per Newman, it is the second toughest challenge to predict weather and climate. So the first one is understanding the brain, how brain works itself. So we are, as a meteorologist, we are trying to address something that is very difficult to achieve, but fortunately, we have access to so many tools, and we are very fortunate that we are actually using all those tools and trying to improve our weather and climate forecasts every day. So, as our secretary always says, that whatever you do, whatever science you do, it should translate into improving the livelihoods of people. So, that is through improving the weather and climate forecasts. So, as you know, that radars will play very important role, particularly mostly in the nowcasting arena, and that is where we are trying to make breakthroughs in the next couple of years that coming. So, with MOS now it's taking up a very ambitious initiative to expand weather radars uh, throughout the India, and as of now, about 40 to 50 radars are in place. And in IITM itself, there are about 8 radars that we are doing research with 8 weather radars. And this workshop comes at a very highly relevant time when we are trying to expand this radar network and trying to create more and more products from the radars. So, as we work towards strengthening our radar infrastructure, it is essential to deepen our collective understanding of weather radar technology, including its fundamental principles, applications, and recent advancements. Through this workshop, we aim to build capacity, train the next generation of scientists. The whole idea of this workshop is to have a next generation of scientists who can carry out and utilize all this vast network of radars that are going to be in place in next couple of years, and use the data and also participate in calibrating whatever way you can contribute. So this workshop is expected to cover all those aspects that are required for advancing the radar metrology in the country. So it is my great pleasure to welcome you all to this national training workshop on weather radar, NT Radar 2025. I think we have conducted before also some of these workshops, and the response was very good. And this time I heard that there are about 100 trainees are participating in this workshop, and about 4 outside experts, overseas experts are giving training, and about similar number from India also giving training for these radars. So I urge all the participants to be very active and ask appropriate questions, and keep no question is a stupid question. Any question is, it may look stupid to you, but the trainer may find it very difficult to answer. So don't think that it is a stupid question first place. So keep firing the questions and keep interacting with the, because you don't get these type of opportunities every day. Having interaction, one-to-one interaction is really helps in understanding these new technologies that are emerging, and also your contribution to the mission MOSAM. That is a very ambitious program that has been taken up by Ministry of Earth Sciences to improve the observational network and also to improve the uh, weather and climate forecasts and make India as weather ready nation. That is the whole idea of that mission MOSAM program. So if you really want to contribute, be serious about this. As I informed you about IITM's uniqueness, as you are going through the training of observations, there is one more batch that is actually going through training of HPC, high performance computing, just above you. There is another training going on at the same time. It was actually inaugurated on last Friday. So here, IITM is, as I mentioned again and again, it is a unique place. You get exposed to several different infrastructures. You feel free to. I hope the organizers have arranged some of these visits to different facilities that are there at IITM. So please utilize them. So get excited with what the scientists are doing and make maximum out of this. So with this brief introduction, I welcome all of you to the city of Pune, and it is really, I don't want to say warm welcome because it is already very hot. So yesterday, the temperature that was recorded here in the same Pashan area that where we are sitting is 41.4 degrees centigrade. So it's really hot. So take care of yourself, be hydrated, take more water, and but make at least the discussions very hot. Okay. So with this, I welcome all of you and thanks for coming and participating in this workshop, particularly Italian colleagues who came all the way to give the training to all of our youngsters. So please make utilize of all these efforts, and I hope at the end of the workshop we'll have a feedback forms and we'll try to understand what all that we need to further improve our training programs. Okay, thank you.
Thank you, sir, for your encouraging words. We humbly request Dr. M. Ravi Chandran, Honorable Secretary, Ministry of Earth Sciences, to address the audience.
Thank you. Very good morning to all of you. Professor Chandrasekhar, Dr. Churi Chandra Rao, Dr. Pandit Rai, Dr. Subrata Kumar Das, Dr. Mohapatra, Dr. Prasad, and the trainers and trainees and other participants, and very good morning to all of you. It is indeed a great pleasure to be a part of this important training workshop. I first and foremost, I thank IITM, especially this, for organizing such an imperative and indeed a needful training at this right time. It is a very important. I thank the organizer for organizing such training. As you all know that the radar is an important tool. Of course, observation is very important to whether forecasting or understanding or many things. Out of observations, the radars are more critical. So we have part of the radar is covered. India is partly covered by, mostly covered by radar. Still a lot more we are planning to do under the mission Mausam. I'm sure by next 1 or 2 years, or maybe by before 2026, we will be having more than hundreds of radar will be operating in India. So at that time, we should have a more number of people trained in radar to various things, either to maintenance and operation maintenance, or you do some of the applications from the radar or some of the nowcast forecasts. So various things we need to understand. So either you take it for validation of rainfall or you take how to interpret the data. Various kinds we need to understand. So more and more people need to be in place. So in that way, this training will be very, very useful. I think I once again I thank the test team. Similar type of training we need to have under the mission Mausam, and it is very important for the entire country. As you talk about the radar, for the first and foremost, from IITM perspective, you should understand the processes, what is happening from the radar for various signals. So we have to look at differently at different people to understand the things what is happening during the monsoon time, especially when radar signals are coming. And this radar is definitely to be a game changer for the, of course, not only for the nowcast, even but also the forecast. It will be a game changer. I think we need to have where we need to place this radar for redundancy, what type of radar we have to put, whether it is X band, C band, or uh, uh, S band, or we need to go for some other phased array radar. So all these things we need to think about this one. So the placement of radar also, I think after this training, I think you should have an idea where we should place, because now we are planning to place it, whether it is redundancy or we need to have multiple radars to look at the cities so that we can have more and more understanding and more mitigation strategy to give the planners. So like that, various safety measures, and we need to have how better prepared. All these things we should understand. So basically, this training, I understand this training will include both operation and maintenance, and also applications, and how do we develop various new understanding and all other things. Of course, this will be definitely beneficial to various stakeholders at the different purposes for one stakeholder for some particular feature is required. So all these things you can make it. Essentially, we need to have more and more such a radar expert in India. And I think it is imperative that my colleagues from trainees, all the people will seriously look into it, and they will be definitely come out with some better understanding. I'm sure at the maybe at 1 year time, we should have at the end of 1 year or 2 year, once all the radars in place, I think we should have a considerable strength in operation and maintenance and application. And also we should have a merged product of radar. The entire country, I should look at one radar image. And also, if it is possible, we can try to merge the product with the satellites and institute various data so that we should have a merged product so that as an operational forecaster or somebody, they can be easily able to serve for the nowcast and other purposes. So with this, I thank once again for the organizer for organizing this. And I'm sure that this training, it is not only one time event. I think frequently we should have maybe once in 6 months, we need to what is called such type of training and other things we need so that we can have some enhanced understanding and a future course of action. So with this, I once again thank you all for organizing this workshop. I am sure that while at the end of 3 days, everyone will take home new knowledge for operating the operation as well as application of radars. Thank you very much.
Thank you, sir, for your encouraging words. We now invite Dr. Mrityunjay Mahapatra, Director General, India Meteorological Department, to share a few words. He's not there? Okay. Is he there? Okay. The next. Okay. He's not. He's not there.
Um, we request Dr. V.S. Prasad, Director, National Center for Medium Range Weather Forecasting, to address the gathering.
Am I audible? Dr. Ravichandra, Honorable Secretary MOS, Dr. Mrityunjay Mahapatra, DG Dr. Surichandra Rao, Director IITM, Professor Chandrasekhar, and Dr. Panditaro and Subhatra Das from organizers of from IITM and other dignitaries, participants of this workshop. Good morning to you all. I feel honored to be part of this radar workshop. And as our Honorable Secretary told, this is the right moment that we have this workshop on radar. As told by Dr. Surichandra and our secretary, that India radar network is expanding exponentially. So that we have about 50 radars, and not only we have many networks. ISRO also having the radars, IMD, IITM, and also different makes, different bands. S-band radar have a C-band radar, and different radars are there. So hosting all these radars and making a merged radar product is becoming very it's a very difficult task. And as far as Surichandra told, that under Mission Mosam, we are expanding this one to about 100 more radars are going to add that one. So all over the country is going to have radars. And in India, we have made many efforts to use the radar data in models, different model system called spectral models and grid model, and we are making use of this lot of data in that one. And from last few years, we mastered our handling the satellite data sets, and at NCMRW, we are receiving almost all satellite data from all over the world, even NOVA, UMETSAT, and for few of the satellites, we are the leaders. Suppose AOLS recently launched CMRWF, the second after ECMWF to operationally use that. And also we have our own satellites, and we have the programs to generate fast area to transfer models. We prove that one. And When I joined, conventional data is mostly is dominating the analysis, and it is having the more impact on the forecast. And at present, you can see the satellite data is dominating, and we are the first two, three satellites sensors having the more impact on the forecast and improving the forecast. And we have seen our own satellites launching. We are able to develop the radiate transfer models and assimilate them and study them, and also design the satellites. And we have the capabilities running the whole observational system experiments. So given that one now radars, we found radars different makes, and we are not able to, we have find, we are trying to two methods to use the satellite radar data. One is by nudging and one by the reflectivity. When we are going to reflectivity things, we are finding a lot of difficulties because the different makes, the quality controls. And or some of my colleagues studied the huge radars that is having the digitometers with them, and we try to derive rainfall and merge with the satellite products. And there are very many challenges we are facing in that one. Not only because of the different makes, the quality of each radar, calibrating them become a bit difficult task. And recently we added high resolution rapid refresh. So we have found that high resolution rapid refresh for nowcasting very useful. And every instead of earlier we are using 6 hours for the 6 hours data simulation cycles. Now because of the radar network what we have, we are started using the radar one every hourly HR high resolution rapid refresh. Basically for using the radar data we design. And the very high resolution 330 meters to cities forecast models we are in place, and we are expecting with this radar data we can improve the forecast and get the nowcasting scales and the expand radars or the hits. We are not able to handle that quality control on that one of the expanded because of reflectivity, the orography that having over the Indian regions. I think that is making complexities. And also, if you see the radar data reflectivity simulation, we found the more than high 30, 40 dBs reflectivity models are not able to handle that. That shows the process studies also has to be modified and because of the physics not able to handle the more than 30, 40 reflectivity, we are stopping at 40 reflectivity. So that shows that there is challenges in developing the physics of physics of the model, radar data, the model, and generating that one. And another thing is we are making satellite radar and gauze thing to make a uniform radar satellite rainfall. Here also we are facing difficulties because of the rainfall retrieval from different channels. So these all tasks, this workshop we hope that will give with international satellite experts and also Indian people are together. And this workshop will give it through a light how to deal with the problems on data assimilation and rainfall retrieval, the nowcasting, and these things we are seeing. We hope this workshop will not to stop here. Many more things IITM and MOS institutes has to conduct because the next 2 years our radar volume is increasing. For example, for data handling. Earlier we are getting the format of the data what we use. Iris data, data volume for each satellite, each radar has substantially increased by the way properly handling packing the data. Recently, we upgraded the data handling of radar data so that we can throw use more volume of the radar data as substantially say volume is reduced without losing the information by properly packing the data. So the packing of the data so that timely in real time it will reach there. We are expecting about this 100 or 150 radars that is coming in the network to reach data assembly and say more, any data assembly center within 1 hour because we are planning hourly update of information. So within 1 hour data should reach that also this all volume of data 1 to 150 radars that are coming in the next few years has to reach that one. We have to plan that one. In the case of satellite, we have the DB network to get the polar orbiting satellite data to receive within 1 hour. And all over the globe, we have the DB network program on the consumer part. We are receiving the all polar radar data within half an hour now, and we are able to use that. So this total volume of the data, which is going to be coming in the near future, we have to plan the data to reach within a half an hour or so to reach the data simulation center, so that we can use in real time data, and also intercalibrating the satellites. Suppose in the US, the radar all are the same way, same type of thing, so they're able to handle that. Now in our network, we are seeing that the radars are different weights, different types, so different bands. So it is giving much more complexity that one. So all radar experts think how to use the different makes and different networks also that one. And also we are seeing different agencies. Suppose ISRO radar data, IITM data are not now being, we are not able to get in real time. So we have to plan integrating the different Navy also is going to radars, and atomic energy, car is also different radars. All these, as a India as a whole, we should get the different organizations having the radars from the tool. Now, Uttarakhand and UP state governments also planning to have radar networks. So it is a big task get the radar data in real time to reach that data. And I of that, I congratulate Pandit Rai and IITM for having planning for this workshop and leading in handling the different data formats and different radars to reach deciding the data, and with ARTs and that Mahabaleshwar radar with high altitude cloud physics laboratory there. We think we have to do a lot of process studies. I hope IITM and experts here will lead country in designing the program. We thank our organizers for giving this opportunity.
Thank you, sir, for
Thank you.
sharing such an inspiring perspective. We now invite Dr. Mrityunjay Mahapatra, Director General, India Meteorological Department, to share a few words.
Namaskar, good morning to all of you. Dr. Surachandra Rao, Director, Indian Institute of Tropical Meteorology. Dr. V.S. Prasad, Director, National Center for Meteorological Forecasting. Distinguished colleagues from IITM Pune, distinguished faculty members, guests, trainees, ladies and gentlemen. At the outset, I congratulate IITM Pune for organizing this program. I also express my deep gratitude to Dr. M. Ravichandran, Secretary, Minister of Arts Sciences, for his wholehearted support to conduct this type of capacity building program. Because of his leadership, able guidance, there has been overall development of the ocean and atmospheric sciences, leading to better understanding of the various processes, and also the improvement in modeling system, leading to the improvement of the forecasting for various types of severe weather events. So when we consider the mesoscale weather events, like say thunderstorms, lightning, hailstorms, gustiness, squall, or localized heavy rainfall events, these events are still challenging for any national meteorological hydrological services, including India. So it has been a collaborative effort among the various agencies in the Ministry of Arts Sciences with leadership of Chandran to address this issue aggressively by jointly considering the observational systems, modeling systems, forecasting systems, and early warning systems. So while doing so, in the last 10 years, there has been significant improvement in detection and prediction of the severe weather events. But still, if we look at the performance with respect to mesoscale severe weather events, that means the localized severe weather events, as I told, like heavy rainfall, thunderstorms, lightning, hailstorms, squall, etc., we have to still improve as compared to our performance for the synoptic weather events. The gaps, what you find that is mainly due to the lack of observations with respect to these highly localized weather events, due to insufficient automated stations or rain gauges, and also the Doppler radars. The satellite has its also limitations because the resolution is 4 kilometers, while there could be the thunderstorm activity within the 4 kilometers, which will not be detected by the satellite. So therefore, there is a need to improve the observational systems, which is being taken care of through Mission Mosam and other various approaches. Especially if we look at various types of observational network and the localized severe weather occurring over our region, the Doppler radar comes a very useful tool to address such requirements. So therefore, under this Mission Mosam, we are augmenting the number of radars, presently 40 radars, and we'll be moving towards 126 radars. So this will enable us to have a redundancy in the radar network. It will enable us to have our presence in the data sparse region, like say hilly areas in the north, in the eastern Ghats, in the western Ghats, Garakasidantia Hills or Myanmar Hills. So by that way, we will have 100% coverage of the country, and also we'll have sufficient data to be assimilated in the numerical weather prediction models. First of all, with this data augmented with automated weather stations, we can have a better analysis to find out the current status of the severe weather event. And that current status itself can be extrapolated to provide the nowcasting for next 1 hour to 3 hours. So finally, we hope that with the augmentation of this network, especially with radar, we'll be able to improve our nowcasting, whose accuracy at present at the district level is 86%. So we have to move towards the location-specific nowcasting, which is being provided at present about 1,200 cities and towns. But we have to go anywhere with the help of drawing a polygon in the severe weather event based on radar informations and other observational tools and model guidance. We can provide the nowcast anywhere at any time. At the same time, the diamond which have come up, that also can be populated, and the 35 minutes forecast with diamond can be provided. Apart from this, as Sad was telling, this data can be simulated in various types of numerical manipulation models, including the nowcast models. We have got two sets of nowcast models. One is the HTTP high resolution rapid refresh model, and also the electrical RF. So what we do at present, actually, we consider both to provide the likely occurrence of the lightning and associated thunderstorms over the Indian region. So I'm sure with the augmentation of this radar data, the assimilation process also will improve, and we'll be able to provide the forecast at nowcasting and very short range forecasting. At present in India, we are not providing any very short range forecast. That means we have got a forecast for 3 hours, that is nowcast. We have got a forecast for next 24 hours. So in between, from 3 hours to 24 hours, say 12-hour forecast, we do not have at present. We can introduce that forecast with the confidence from the various numerical modeling systems in this range. HRRR is being run for next 24 hours, and 72-hour forecast is being generated from EWRF, and this provides every hour forecast. So therefore, we can introduce, once these models are validated with a high amount of data and the ground truth. So that will enable us to have really a seamless forecasting system from say 35 minutes in the Imini to 3 hours in our Navcast system, then very certain forecast for 12 hours, and then 24-hour forecast, then 72-hour forecast, 120-hour forecast. Then, of course, we have got the external forecast and seasonal forecast. So, therefore, severe weather event we are targeting of to medium range. That is, we identify the potential area at present, say 7 days in advance or 5 days in advance. Then we went on gradually 3 days in advance. We should identify the districts which are likely to have potential severe weather events. Then we come to the day of occurrence there. Now casting and very short range forecasting will help us to improve our efficacy and service delivery to all stakeholders, including the common people. I'm sure this training program will be very helpful to improve the capacity building in all aspects, starting from the observational systems, modeling systems, data assimilation, and forecasting, and early warning. I thank Dr. Surijan Rao for taking this initiative. And once again, I express my deep gratitude to Dr. Ravichandran, Secretary of All Sciences, for uh, providing the leadership for carrying out this capacity building program. Pandit Rai has been very helpful to India Meteorological Department at any time, whenever we go for any kind of support in terms of instrumentation and with respect to radars or with respect to any other instruments. So for which when we need some technical expertise and advice, it was handy and it was available without any hindrance from Dr. Punit Rai. And this radar training network being conducted when Dr. Punit Rai is retiring from service is the best tribute to Dr. Punit Rai. I wish him all the best for the future. So thank you very much.
Thank you, sir, for your inspiring and encouraging.
Yeah, well, Mike.
Can you hear me? Okay. I don't know if the secretary is still online, but this is a course about radar, but also somebody told me Dr. Panditurai is going to retire soon. So I tried to narrow the focus. And IITM is very famous for few things like modeling and microphysics. So these are two strong areas here. Though I don't want to do too much about modeling, and that's for some other time. When we talk about data assimilation and radar, that's a whole another topic. We'll save that for some other time. But microphysics will keep focused. And then somebody told me Panditurai is going to retire. So when you go to some party, then I will tell you later that then you compose a new song for the event or make a new poetry. But what is it? We will do similar. So I have something. So then I went and picked. This is Panditurai as he looks today, and this is. I heard this picture was taken about 5 years ago. That's a joke, but that's almost the time when. Can people recognize this person here? So, huh? Yeah, I don't know if he's the secretary is online, and but I thought I'll bring this picture. The key point is, looks like he has just aged by 5 years from the time he joined to today. So we all have to learn from him the secret of his youth. We have to find out his food habits and everything else. Okay, with that, I wanted to give a focus on microphysics and radar. And then in the old days, everybody talks about radar reflectivity is d to the 6. D is diameter. That everybody just thinks like that. How many of you are really almost new to this field? Please raise your hand. Good. Good number. I think that person didn't even, the one behind. Is he a technical person or is he in class? Are you in class? Are you in class or technical support? Okay, good. Then he can stay there. Otherwise, I'm going to, if you have, I have to be able to see you. I am a professional teacher. I know how to harass the students. So you will see that strength coming across. So, but very soon people found the spherical assumption is not valid. It's all given by Rayleigh scattering. So now these precipitation particles are nowhere close to sphere. So then what we did was look at this date, 1984. It's first we started built the first dual polarization radar for research. So we started in 1982 and 84. Uh, we started putting out first pictures. It's like what we call as baby pictures. And you can see this is a picture of reflectivity. See the date, it's 1984. And this is in Colorado. In Colorado, 18th May is about the time spring transition. I mean, winter transitions to spring, and then so you can start thinking about rain on the ground. At this time, people used to send balloons, and then using sounding systems invented by Professor Vaisala, nobody knew the transition from water to ice. There were old radars, weather service radars. There were reflectivity only radars. Chennai airport had a radar. Mumbai had a radar. They all measured reflectivity. They would just see this. But then this is a dual polarization picture. This is 1984. There was no internet. There was no fancy. This color picture was taken by a color photo, not by some fancy color printer. No internet, no high performance computing, nothing. This is a display, raw radar display. In a raw radar display in your face, without any fancy processing, you can see the distinction between ice and water at 1.5 kilometers is the melting layer. This is the huge success story of dual polarization radar that gave the whole revolution of transformation to dual polarization radar all over in the world. In fact, I still remember coming here and then trying to preach dual polarization radar. It took till almost year 2000 for even India to accept. But this today, you cannot even buy single polarization radar if you want to. Every manufacturer makes only dual polarization radar. It has a lot of other advantages, that's besides the story, but it is driven by microphysics. We all have to remember that. And that's the first part of the story. Just knowing the difference between water and ice tells a lot latent heat calculations. Let's go forward. Then, first of all, whenever you come up with something like this, we were all lucky. I'll be honest with you. We just stumbled upon this when we make observations. Then people don't believe. They said this is some freak phenomena that happens in Colorado. I don't think you will see it at other parts of the world. So at that time, uh, in 80s, there was a lot of money for research. So they gave us a lot of money to move a big S-band radar to some other part of the US to show that it still works. So we moved this radar from Colorado to Huntsville, Alabama. And you see how tall this storm is. 18 kilometers. It's tall storm. I think many of you fly here. So do you know what height Indigo flies with the airlines? Somebody from the student side, can somebody answer? How much? 9 to 10 kilometers. Do you agree with him? The red shirt, you are shaking your head. Yes or no? You agree? Good. So it's about, yeah, answer, it's about 30,000 feet. You know, in aviation, they still use feet. It's double that height. So obviously, if you see a storm like this, and of course, other parts of the India, this is, and then then we started looking at things. You know, the La Plata region in Argentina, we were just there doing some experiment. They have the tallest storms in the world, so we will get to that. But then the Kal Boishaki storms in India, I have heard from, again, looking at satellite data, they have the second highest storms in the world. But again, this is statistics. This like competing with Cherrapunji has the highest rainfall. Then sometimes you find that Bombay has more rainfall than Cherrapunji. Then what's the meaning of that? So it's in that spirit. Take it. But these are these tall storms, and also here you can see the melting layer, and it's about 5 kilometers in Huntsville. So we never looked back. So this is the 1.1 of the microphysics story. Then I think this was done in Renzo's thesis work. So this is that. Then you go forward, forward, forward. The DG was talking about products. Now we create products and then make a path. And this is time 37:45. See the time resolution. This is a street map of Dallas Fort Worth area, Texas. We actually produce a hail swath along the path. This is where the hail is going to hit. And so that's the pen sitting here, Renzo Bikini, his thesis work. And this is in Dallas Fort Worth. So that's how far we have come. Then see this, that's the shape of a raindrop. So what I did is, okay, we are coming to this meeting. So we have to have our own poetry in honor of this meeting or compose a song. So what I did was I called up my friend. I ordered a raindrop. Seriously. So there is one institute in Hyderabad, Indian Institute of Technology, where they will make raindrops in a wind tunnel. I said, look, I am ordering a raindrop. Take a picture, and I want to see the oscillation of the raindrop. because that's what originally initiated the dual polarization research. So this raindrop was ordered for this event, and music on. Hello, I need music. I spent time putting music on this. Music, music. Otherwise, I'll start singing. So this is a 3.5 millimeter raindrop to be named Pandi. And at the raindrop research facility, you see raindrops are oblate spheroid shaped. So if somebody asked, they say that's the shape of idli, but then it oscillates like this as it falls. Audio. Audio is not coming. That's why I wanted to play on. Yes, we can dance with the raindrop. You like the music? So this raindrop was created for this event, and in honor of this workshop and in honor of Panditurai. So that's the closest I could get to for creating a poem for this event. So now you know you can. There is a place in India you can order a raindrop. How many of you knew raindrops look like this before? Good. Who is seeing the picture of raindrop for the first time? Raise your hand. Wow, it's very good. See, you learned something new today. So if you had the ability to actually see the raindrop when it falls, this is exactly how it looks. So this is captured in a wind canal. This shape of raindrop is what drove dual polarization research in microgrids. So this is what all the radars will see that control the rest of the technology that is made for dual polarization radar. The problem. Huh? Oh, it has the concert effect. Okay. The next thing is raindrop size distribution. Last of the early talks, I'm just going to make some jokes here, so don't take it too seriously. They were talking about ZR equations. That is also in India, it's called the ZR equation. That's like international fraud. But we all do that because we don't know what else to do. That's because that's an engineering solution. When you don't know anything, take x versus y and make a regression, whether it's a straight line or not. We will fit a straight line and then try to come up with an answer. So that's what we did. And so what happens is you will find that the same reflectivity comes from different raindrop size distributions, and then they have the same rainfall. For example, there are 5001 millimeter drops and 74 raindrops that are 2 millimeters. They both have same reflectivity, but one has 35 millimeter per hour rainfall, the other one has 6 millimeter per hour rainfall. This is the problem of estimating rainfall rate today. The rainfall microphysics and then the rainfall as a product, that's an engineering issue. We have hydrologists who take that input and then run it into models, and they have to make flood forecast. But rainfall comes as raindrops as distributions, and they have produced different types of space-time structure. This is why this has been giving the big challenge. So to solve that, raindrop size distributions and the same rainfall can be also reflectivity can also gotten by 4 millimeter raindrop. The picture I showed you before was a 3.5 millimeter raindrop. So it produces a lot of reflectivity, but not much rainfall. So this what is done is this is all fit with a typical ZR relation, and then but that was not enough. So that drove to dual polarization. Whereas what you do is the same differential reflectivity, you can you can stratify the data with different DM, that is D zeros, which is drop median diameter, or different DM, that is drop mean mass diameter. Then they align a little bit better, and then they contribute towards better rainfall estimate. This is another big advancement that came from microphysics focus and radar. So I wanted to highlight that part of the story also. Then if we keep going, so this is the if you fit a ZR equation, it'll just draw one line through everything. Then you just come up with some number. That's all. So then the third big process is precipitation process. So there are people here who study that to extreme detail. So everything in precipitation process can be, by the way, this is very important. Nowadays, have you all heard of flipped teaching or flipped classroom? You know, in the olden days, classroom is you just keep on lecture, people are sleeping, awake, nothing happened, nobody knows what's going on. Now the focus is not on teaching. What's the focus on? Learning. So all the material you will see here, I will show teaser pictures. You have to take notes. No PowerPoint slide after the lectures. If you're not paying attention and if you're seeing the cell phone, that's the end of the story. So because a lot of people look at cell phone thinking, I'll go look at PowerPoint slides later. No PowerPoint slides. And then if you want to learn more, you have to go read the book. So a lot of the figures and pictures are from this book. So I am a professional teacher and this is a class. So we have to run this like a class. Not so there has to be some sort of responsibility from the students to learn the material. Otherwise, all of us are wasting our time. Okay? So I will be paying attention to all of you. Then people are wondering, oh my God, what did I sign up for? Anyway, the key thing is the vertical structure of reflectivity, differential reflectivity at different parts of the storm can be connected to a whole bunch of things, all the way from fragmentation, splintering, secondary ice growth, collision, coalitions, condensation, drop breakup, mixed phase, everything. So it's just a big playing field for all the microphysicists here. Precipitation process, it's beyond microphysics. Okay, then I could talk about the national coverage. Again, this is the national coverage. National coverage of radar in the US. It's about 150 radars. And then we talked about there is another part connected to uh, Pandit Rai's legacy here, which is the X-band radar network for the city of Bombay or Mumbai. So this is I am showing this is city of Dallas Fort Worth, where we had a network of 8 radars, and so we ran a big experiment, and this is all came from the CASA project. And I will talk about why suddenly X-band came into picture. And then here is a TV news person explaining the role of X-band much better than what I would do. Let's see, audio problem again. We need audio.
Headquarters.
Oh, good, good.
World News. The National Weather Service now says the damaged more than 100 homes in New Hampshire was a tornado. This has been an especially violent tornado season with 120 deaths, nearly twice the number in an average year. The toll could be reduced by giving more advance warning of tornadoes. A revolutionary new radar system promises to do just that. Here's ABC's Ned Potter.
No matter where the storm strikes,
It's a tornado.
people say the same thing. If only they had had the slightest idea.
It was so fast. It wasn't even 5 minutes.
It happened again yesterday with the storm in New Hampshire. The
The
U.S. has
US,
the
US,
fastest radar network in the world called NEXRAD. But even so, the average tornado warning comes only 12 minutes in advance, and 3/4 of the warnings are false alarms. Which is why researchers are working on the next generation of tornado warning technology. They call it CASA, small high-tech radar like this one in Oklahoma that can be mounted atop buildings or even cell towers. Combined with powerful computers, they should eventually be able to tell you whether your street will be in danger, something NEXRAD cannot now do. NEXRAD is so powerful that this antenna can see for 250 miles, but it can only see in a straight line, and remember, the Earth is curved. So there may be a funnel cloud 50 miles away, but this antenna cannot see whether it's touching the ground. But because CASA is so much smaller, you can dot the country with as many as you need, filling in the empty spaces between NEXRAD domes. And since they're closer to the action, they can see much more detail. Here's a NEXRAD scan of a storm front moving through Oklahoma, and here's the same thing seen by CASA. The old NEXRAD, the new CASA.
Can you hear me now? So you can see this is you have this X-band radar network. I'm making jokes here. In Mumbai, then one day you will be able to make the same talk that look at this radar from IMD. It's so slow, 5 minute scan. Look at this X-band radar network, just fast update in city of Bombay. Hopefully, there is Sachin or one of you guys can all make a talk like this with Mumbai network. So with all this, I like to just give teasers for the legacy of Pandit Rai and all his colleagues in IITM for the focus on microphysics, precipitation process, and radar meteorology work. And then I will end here. Thank you. I think we should go to the next talk. We're not doing questions now, right? Okay, good.
Thank you, sir, for the insightful and engaging talk on the evolution of dual polarization radars and technological advancement in measurement of microphysical properties of precipitation.
We now invite Dr. G. Panditharai for his keynote talk on IITM's initiatives on implementing radars for cloud and precipitation process studies.
Hmm? Very, yeah. Screen will never happen. I know. Yeah, 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 yeah. Yeah, good morning, all of you. First of all, I welcome you all to this workshop, um, especially the resource experts, Professor Chandrasekhar and Renzo, Dr. Renzo, and Dr. Baldini, and I forgot other names, third name. Yeah. So, and all other experts from within the country and all the participants. I'll just quickly go through the um, my talk, which is IITM's initiatives in implementing the radars for cloud and precipitation process studies. Um, Almost last 15 years back, IITM put a seed in uh, implementing the radar. Earlier, radars were available only with operational weather agency. For us, it's India Meteorological Department. Um, so I'd like to thank all my colleagues, senior scientists, and the PhD students and project scientists for all the contributions to this project. So here I'm giving a chronological order that how the IITM entered into radar research. So we started with the orographic research testbed, which is started in 2012. So at the same time, we were also, entering into a radar meteorology. We had a magnetron-based X-band radar, which was deployed in the Western Ghats to study the orographic precipitation and the orographic convection. We also augmented later a cloud radar to look at the cloud to rain transition processes. Then the other project, which cloud aerosol interaction and precipitation enhancement experiment, wherein so the radar was required for guiding the cloud seeding operations. I think the project director was Dr. Taras. She was here. So here, a dual pole C-band Doppler weather radar was deployed in Solapur, which is a rain shadow region. So wherein the cloud seeding operations were carried out, the radar was able to guide the cloud seeding operations. Then recently, a few years back, we also set up a atmospheric research test bed in central India, which is a core monsoon zone, to understand the monsoon convection processes and the monsoon zone. During monsoon, we get a lot of low pressure systems and a lot of various synoptic systems which form in head Bay of Bengal, pass through this region, so which in turn give extreme rain events. Here we commissioned a dual pole C-band Doppler weather radar in co-location with several other observing systems. Then very recently, with Professor Chandra mentioned that we established a small X-band radar network in Mumbai metropolitan region to provide high resolution rainfall, both the temporal and spatial, to enable flood warning and nowcasting applications. So I'm just showing this picture with Professor Chandra and my colleagues, senior colleagues. I think some of the junior colleagues are missing in this picture. I'm sorry. So each of them take up uh, different projects. I think some of my other colleagues used to call, okay, the different frequencies. They work on different frequencies. Some work in K band, X band, C band. So in Hindi, one of my colleagues used to say bandwala. This project is a bandwala because they work in different frequencies of radars. So, and my outline of my talk is I'll just give some glimpses without taking much time in, before the tea break. So we work on orographic convection and precipitation processes, then the core monsoon zone convection and precipitation studies using weather radars and urban weather radar network. The first one is that we started in somewhere in 2012, mainly to understand aerosol cloud precipitation interactions and also to understand the orographic clouds and precipitation. If you look at here, this is the Western Ghats, and you see a heavy precipitation region here. So if you zoom this Western Ghats, so you'll see this is the color shows the elevation data. So as high as it can go up to 2.6 kilometers, and mainly during southwest monsoon, we have southwesterly air masses, moist air masses when it uh, impinges on the Western Ghats mountain, and you have a forced condensation which leads to enhanced collision coalescence process and also droplet growth, in turn the which accelerates the warm rain process, which leads to this heavy precipitation. So here to address this, we deployed both X and K band radar, and this is our radar site. What you see here is a star, and the X band radar coverage is about 125 kilometer, and K band radar can only look at up to 30-kilometer range. And these are the technical specifications. What you can notice that if you want to study the cloud droplet, so you also need to probe with the millimeter wavelength radar. That's what you see. One is in centimeter wavelength, which is for raindrops, and the other one is for cloud drop observations. So see here, this is the elevation or mountain elevation, and if you look at the convective cell spatial distribution within the radar domain, you can see along the mountain slopes. So you have the congested cells are most abundant, and you will notice that deeper cells are more frequent over leeward side. Um, Also, if you look at the diurnal variation of different types of convective cells, you will note that the congestus peaks about 14 hours local time, whereas the deep convective cells peak around 16 hours local time. So for such a transition, you notice a lead lag relation. So for such a transition, we need a mid-tropospheric moistening and heating by congestus is very important. So same convective storm, if you look at with the two different frequencies, what you see here is from X band radar, and the same one if you look at with K band radar, then you will see the further fine structures of cloud droplets. So this is the one of the vertical structure of a storm. So you can see that the convective clouds can extend up to 16, 17 kilometer over Western Ghats. And now I'll move to the research testbed wherein we deployed radar. And what is the importance of this core monsoon zone? You can note that there are synoptic systems which form in head Bay of Bengal, moves towards this core monsoon zone and produces um, extreme heavy rainfall events. So this monsoon trough, uh, which comprises of this core monsoon zone, is one of the important semi-permanent systems of the regional monsoon system. This is the in this region we call core monsoon zone. If you correlate the core monsoon zone rainfall with all India summer monsoon rainfall, you will see a high correlation. So if you can improve the prediction of rainfall variability in central India, so you'll be able to project onto the larger scale predictability. So with this, we set up this. It is our dream is to make this atmospheric research testbed similar to United States Department of Energy's ARM facility, which is, if you are some of you may be familiar, atmospheric radiation measurement facility in southern Great Plains in USA. So similar to that, we need to have something similar in tropical region. So this is the core monsoon zone wherein this dual pole C-band Doppler weather radar is installed. And in addition, we have a whole suite of other instruments to study the precipitation, clouds, radiation, and other vertical profiles through balloon soundings. So we deployed several equipments over this atmospheric research testbed site in central India, which is about 50 kilometers from Bhopal city. So you are so those who are interested, you can visit there anytime. Our scientists are there, so they will take you a demo. So idea is that how these observations, co-located observations, could be used in a single column model, which in turn it can be tested, validated, and we can improve the three-dimensional numerical weather prediction model. So that is the idea of this. And this is one such how the convection scattered convection gets organized into a squall line type of thing. That's what you will see in this region. So this isolated convection gets organized and form like a squall line and move towards this region. So this is one of my colleague. He was looking at Murali Krishna. He's looking at how this is the radar domain. You can see the extreme rainfall events are observed in southeast to northwest direction in the radar domain, and this is uh, the frequency of extreme rainfall events. And also, if you look at the storm area and the reflectivity, the the storms are of mesoscale convective systems um, in the radar domain. The vertical extent of extreme rain events can limit it to 12 kilometer over this region. So there are two peaks you can see. There is a um, primary peak at 7 kilometer and a secondary peak at 10 kilometer. So this is one of the extreme rain event happened in 2022. So you can see that this is from GPM iMerge data, and this is the in situ disdrometer data. But the differences in rain accumulation could be due to the gridded averaging in the um, satellite data sets. And so Professor Chandra mentioned about the capability of polarimetric weather radar data. So this is one such example. So this 22nd August was one of the extreme rain events. About 200 millimeter rain occurred in central India. So what you notice here is that the clear transition between warm rain and the cold rain processes, and well-defined signature of the melting layer, and you can even also see some undulations of this melting layer. So this gives a lot of information about the microphysics processes, which you will be learning through this workshop, how to interpret these polarimetric radar data into um, the rainfall microphysical processes. Then I'll move to quickly to the our country's first urban weather radar network over Mumbai metropolitan region. You all know that the world's urban population in 2023 approximately about 4.6 billion, which is 57% of the global population. The UN reports suggest that the urban population will increase to 5 billion by 2030, which is 60% of the global population. Where Mumbai is one of the most populated metropolitan areas in the world, with a population of over 26 million. It's also vulnerable to flooding and also tidal issues due to its location along the Arabian Sea and low-lying coastal areas and several reclamation projects. So the rising sea levels also due to climate change are expected to worsen these flooding issues. So we initially started with a rain gauge network, so which we were giving real time to the people and also the flood warning applications group. These are our rain gauge data, so one can look at it. It is shared in even mobile applications, so one can also access through a mobile application or this is a web server. These are some typical displays of real-time automatic rain gauge rainfall. Then we also thought, why not we have a high temporal spatial resolution um, rainfall information through a urban weather radar network. So that's how we um, implemented this project. So so this is how the operational weather radars, which are very huge, which needs a lot of infrastructure to set up a radar. And also, you can, as Professor Chandra mentioned, that you will not be able to see after certain ranges, the lower part of the atmosphere where precipitation has to be observed in the lower atmosphere. So, so like tornado, he mentioned that it's not even looking at the tornado; it's seeing about 4 kilometers. So this principle, so utilized here, and we put four uh, short range Doppler weather radars X band in four different sites. So spreading from south to north. So each of them are separated about 30 kilometers. Um, and this is, so if you want to look at closely, there is a control room. And so it is inside the radome what you are seeing, how the radar spins. And they're all operating in X-band frequency, which in the workshop he will address why the more and more the people are going for X-band radar nowadays. And these are the four radar network, and there is a overlapping between these, so that we can, if one cannot see, if one radar is getting high skyscraper obstruction, then the other radar can be able to supplement this data, and we can make a mosaic. So these are some of the installation procedure which was where people put a lot of effort to move these radars in a heavy traffic regions, and set up these four radars. And this is a radar configuration. We have all four radars set up, and then we have a central server here, and also a display station in each of these radar station. And we have a mosaic server at IITM. The mosaics are created from the four radars. These are some of the typical cases which expanded our from the last monsoon season. We just formally inaugurated in the last monsoon season. So these are some of the initial data sets uh, from the radar mosaic. And I think you will learn through this workshop, during this workshop, that how these um, radar reflectivity and radar polarimetric variables are utilized to convert into radar rain rate. So with this, I'll summarize here. And so radars play a major role in understanding cloud and precipitation processes, and in turn Earth's water cycle. It also helps improves the forecasting of extreme events that cause natural disasters. Presently, IITM is augmenting an X-band radar in Mahabaleshwar, which is a Western Ghat region, and it will be operational soon. In atmospheric research testbed in core monsoon zone is being augmented with a dual frequency cloud radar. So we are working on to put a dual frequency Ka and W band radar. IITM is also working on expanding the urban weather radar networks in Delhi and Chennai in coming years under Mission Mausam project. So with this, I will stop here, and um, thank you all. So wish you all a good stay in Pune, and have a good workshop and interact with the resource experts. So thank you all. And also there is a scientific film which are given here. Maybe sometime people can play these movies to them so that they will appreciate that. Thank you. Thank you.
Thank you, sir, for the enlightening presentation on IITM's initiative and highlighting the pivotal advancements in cloud and precipitation process studies.
We now invite Dr. A. Surachandra Rao, Director IITM, to kindly felicitate Dr. Pandit Rai. So if you could just please stay on the stage. We are privileged to honor Dr. Govindan Panditharai, whose pioneering contributions over more than 3 decades have profoundly advanced our understanding of atmospheric processes, particularly in the fields of aerosol cloud precipitation interactions, atmospheric radiation, and radar remote sensing.
Dr. Pandithurai holds a master's degree in physics from Alagappa University 1987 and earned his PhD in atmospheric sciences from University of Pune in 1998, specializing in aerosol studies using LiDAR and radiometric techniques.
He began his journey at the Indian Institute of Tropical Meteorology, Pune, in 1990 as a senior scientific assistant and has since built a distinguished and inspiring career, currently serving as Scientist G and Project Director of the Atmospheric Research Testbeds Project.
Over the years, Dr. Pandithurai has led impactful research nationally and internationally, collaborating with institutions such as University of Maryland, USA, and Ceres, Japan.
He's been a pioneer in atmospheric aerosol research, developing innovative retrieval algorithms, establishing India's first Skynet site, and providing key observational evidence for aerosol radiative forcing and cloud aerosol interactions.
Dr. Pandithurai has been instrumental in establishment of several atmospheric research facilities of IITM across India. He played a key role in setting high-altitude cloud physics laboratory at Mahabaleshwar, designed for detailed cloud microphysics studies. He also established X-band radar and cloud radar observatory at Mandardev.
Dr. Panditharai was instrumental in establishing the Atmospheric Research Testbed at Silkhera, Madhya Pradesh, a long term observatory dedicated to land atmosphere interactions and monsoon research.
He also played a key role in setting India's first urban radar network in Mumbai, comprising of four short-range X-band polarimetric radars for high-resolution monitoring of rainfall and convective systems in urban settings, marking a transformative step in urban hydrometeorological research.
His contributions have been recognized through several awards and honors, including the Certificate of Merit from the Ministry of Earth Sciences, IITM Golden and Silver Jubilee Awards, Dev Raj Sikka Best Paper Award, Das Gupta Award, and JSPS Fellowship from Japan. He has also served on several expert panels in MOES, ISRO, and other agencies.
Dr. Pandithurai is also a dedicated mentor and educator, having guided 14 PhD. He published more than 180 peer-reviewed papers and has H index of 34.
Dr. Panditharai's unwavering commitment, intellectual rigor, and passion for atmospheric sciences continues to inspire the next generation of researchers. It is with immense pride and gratitude that we felicitate him for his invaluable services and enduring legacy in the atmospheric research.
First of all, I want to thank you all for felicitating me here at this August audience. And I think we have a lot of visitors from outside and also from across the country. The participants have come here, and I'm really honored to have this felicitation here, even though I have still 50 more days to go in IITM. So thank you all again. So.
Thank you, sir.
you so much, sir. Now we request Dr. Subrata Kumar Das to give us an overview for the workshop.
Namaskar and good morning to all and everyone. Uh, Respected Honorable Secretary MOES Dr. M. Ravichandran, Director General of Meteorology, India Meteorological Department, Dr. Mrityunjay Mahapatra, Director NCMRWF, Dr. V.S. Prasad, Director IITM, Dr. A. Suryachandra Rao, Professor V. Chandrasekhar, Distinguished Professor, Colorado State University, Dr. G. Pandit Rai, Project Director, Atmospheric Research Station at IITM, distinguished faculty members who join us for this workshop, IITM colleagues and friends, and all the participants joining us both in person and online. So it's my pleasure to be part of this anti-radar workshop, and this is a 4-day training workshop organized by IITM Reach Out program of the DEX. And this training workshop will aim to build the technical capacity in the weather radar system, particularly focusing on the dual polarization radars and their diverse meteorological applications. So glimpse has been shown by Professor Chandra in his lead talk you have seen. So more detailed discussion will be there in the upcoming technical sessions. So this technical session we have specifically designed to have a basic and comprehensive understanding of radar system from very fundamental level to a very advanced level, covering theoretical foundation, calibration techniques, scattering mechanisms, signal processing, and finally the meteorological applications of the weather radar and also the radar application in the urban hydrology. So this training workshop will closely follow the very few books are available in the weather radar, polarimetry radar. So this training workshop will follow the newly published book on weather radar as Professor Chandra was showing, Introduction to Dual Polarization Weather Radar, Fundamental Applications and Network. And most of our technical session will be aligned closely with this textbook. And we have very privileged that the author of this book is a part of our distinguished faculty. So you can have a very good time to ask several questions and doubts, so they are ready for you. So key feature for this workshop is that every day we will have hands-on coding exercise and recitation sessions, providing participants with the practical experience in the radar data analysis. So it is not only that someone is coming and giving a lecture, so there are computers we have kept and internet is available. I request whoever has bought the laptop, they can also use. So some there will be the practical coding analysis, some data set will be given and they will show how these things, for example, the attenuation corrections or like yeah, rain estimation from the radar, these are all challenging things. So we have a very fortunate that our esteemed speaker is going to help us in showing those practical applications and doing those coding exercise. And another major highlight is the radar site visits, which we planned on the last day of this workshop, which is on the April 10th, where the participants will have an opportunity to see the live radar operation. So whatever we have learned in the day one, you can go and see that where is actually this radar is happening, and then you can interact with the experts and discuss the real world applications of the radar technology. So as a director was mentioning for this workshop, there is an overwhelming response means showing that there is a growing interest in the radar metrology. So we have received nearly 300 applications for this workshop, which is the highest in the IITM. Till now we didn't receive this much. And initially this we thought like there will be 50 participants, but we have seen there are so many requests, it was very difficult, and so now there are more than 105 participants attending this workshop. And to encourage the further participation, we are also doing the live streaming of all the technical sessions, including the inauguration. So on behalf of this organizing team, I warmly welcome all the participants to IITM. We hope you have a rewarding experience, gain valuable knowledge, and try to engage in discussions with the radar expert. As the director sir was mentioning, don't hesitate to ask the questions because they came here and they are trying to teach you to learn as much as possible from them. Wishing you all a wonderful and a productive workshop. Thank you.
Thank you, sir, for laying out the roadmap of the workshop. Now I invite Dr. Shikha Singh to deliver the vote of thanks.
Yeah. On behalf of the organizing committee, it is my privilege and honor to deliver the vote of thanks for this inaugural session of National Training Workshop on Weather Radar, organized by DESC IITM. First, we extend our heartfelt gratitude to the Director IITM for his continuous guidance and unwavering support, which has been instrumental in bringing this workshop to a reality. We are extremely thankful to Secretary MOES for his telepresence, even in his very busy schedule today. Thank you, sir, for joining us and delivering the message. We are also thankful to DG IMD, who graciously accepted our invitation and addressed the gathering with us via his telepresence. We thank the director NCMRWF for his participation and addressing the gathering. We would also like to extend our sincere gratitude to Professor Chandrasekhar, uh, whose unwavering support, guidance, and vision have been instrumental in bringing this workshop. This workshop would not have been possible without his insightful contribution and commitment to knowledge sharing. A special thanks to Dr. G. Pandithurai, Project Director Art, for providing his continuous support and encouragement throughout the planning and execution of this workshop. We are immensely grateful to our esteemed speakers for accepting our invitation and bringing their vast expertise. Our sincere thanks to MOES Reach Out program via desk at IITM for providing all the support and funding for this to conduct this 4-day training program on radar. We also thank MOES for getting all the necessary clearances for our international resource persons. The dedication from desk in coordinating logistics and ensuring seamless in-person and live streaming is truly commendable. A heartfelt thanks to art group members for their valuable discussions, constructive feedback, and support in making this workshop a success. Your contributions, both direct and indirect, have been vital in shaping this initiative. We especially thank the Computer Division, LIP, Accounts, Administration Office, Guest House, Prithvi Hostel Administration, Security, and all the LOC members for their tireless efforts throughout the workshop. And lastly, a special thanks to all our participants who have traveled from various parts of the country to be a part of this workshop. Your enthusiasm and willingness to learn is what truly makes this event meaningful. Without you, this workshop would not have been possible. Hence, please have a productive workshop. And as Professor Chandrasekhar already said, that it is going to be an interactive session, so make the most of it. With that, we once again extend our heartfelt thanks to everyone and look forward to a fruitful workshop ahead. Thank you. So, may I now request everyone to move to the front of the auditorium for a group photograph, and this will be followed by a high tea at the basement of this hall. So, the technical session starts at 11:30. So, I request all of you to be in time and start and have a punctual start. Thank you.
Since start recording, sir, there is one thing. Online people will be also maybe asking questions.
Sure.
So they will be
Okay.
repeating it.
Okay. Okay.
Shall I? उनका mic पे चल रहा है। Good morning, everyone. Welcome back from the tea break. We have a few logistics announcements. Firstly, for those who would like to claim the travel assistance from the organizers, the TA forms are available at the reception desk. You may collect it and submit it at the reception with necessary documents while you are here for the workshop. The lunch and refreshments arrangements are made at the basement of the auditorium. The lunch coupons have been provided to you. Water dispensers with disposable cups are kept outside the auditorium. We have kept 10 computers in the front row of this auditorium. Those who do not have laptops may use these PCs. Lastly, the workshop bag and the water bottle will be sent to you tomorrow morning. The workshop bag and the water bottle will be provided tomorrow morning when the inventories arrive. Now I invite Dr. Pandit Rai to act as the moderator for the session.
Yeah, welcome back after the inaugural session. I'm the first technical session is being started by. So we are the title of this first session is Fundamentals of X and C band radar systems. And we have all the resource experts here, Professor Chandra and the entire team, um, uh, Dr. Bachani and uh, Baldini and Timonani. Yeah. So, Roberto. Okay. So, with this brief introduction, I'm handing over to Professor Chandra. So, he will um, take this session forward. Thank you.
Hear me? Yes. So very seriously, how many of you are doing this radars course for the first time? Raise your hand. That's very good. So, which means we should teach this very properly instead of trying to show how smart we are. So, and some of you are veterans. You know, this is very important because we have to say, know your customer. And so you are all important customer, but then we are also high value customers like IITM. Then please raise your hand if you have already decent knowledge about radars because you are part of IMD, IITM, or some institute. Please raise your hand fully. I want to do survey. So three, but you raised your hand on both sides, no? No. Sorry? Can you speak up? Okay. You are okay. Good. So with this, we will. Who has traveled the farthest to come here? You? You? From where? Kashmir. Wow. Cool. You? Kerala. Oh, that's not too far. Actually, I travel. Trivandrum. That's Kashmir is still farther. Somewhere else. Who is Jaipur? Good. Yourself? Who's sitting there very far away? Then you should come forward. Okay. All of you, please come forward because I am a professional teacher. If you are looking at your cell phone, I am looking at you. Don't be mistaken, and I will say this. Okay, now with this, there's a lot of stuff we can talk about radars. One of the things I find is I get a lot of papers and reports from India, thesis to receive, and they don't understand what's so special about X-band radars and why it took so long for X-band radars to work. So a lot of the emphasis will be today on why it was not, it was small, cheaper, why we didn't do this before. Before we do that, I want to introduce our team. See, that's me. And we have put in a lot of work on this class. So because of that, I want to make sure that it's not like we just said, oh, can you come give a talk? Okay, let me see what all slides I have. Collect all these slides, start talking. No, we prepared a specific course syllabus, pedagogy, and then I gave a lot of hard time to Subrata. He was about to run away from teaching, organizing this class. I gave him a lot of hard time. And in no particular order, Renzo Becchini is all are associated with not loosely, they are actually formally associated with the CSU and ARPA. Can you come forward, Renzo? Give him a big hand. Roberto Cremonini. So give him a big hand. He is also affiliated with CSU and ARPA. And our grandpapa, Luca Baldini from CNR. CNR is National Research Council of Italy. They are from different parts, but we have had long-term collaboration. Then, so all of us have worked together and worked a lot of time on this. So we actually are a team. And if you have a bandwala, this is our band. I am the orchestra conductor, which means I just shake my hands. They do all the playing. So with this, please take a seat. So I will just teach the first part and then they will teach the rest of the class. Okay. So radar, the part of this picture is to show historically you have seen, especially for those who haven't listened to radar before, radars, people always talk about the word reflected signal. That's wrong. You can see what is going there. It's when the electromagnetic wave hits, it travels in all directions. You know, during inauguration, somebody gave a coconut. I thought somebody was going to break it on the ground. When you break coconut on the ground, what happens to it? It scatters. Exactly the same thing happens. And so a small part of it is coming back. And so with that, you figure out everything that is happening. And if a lot of people think military radars are hard, we are very lucky because military invented and invested in all that technology in the radars, but the meteorology community is benefiting from that. But meteorological radars are much more complicated than the military radars. The reason is because in military radars, let's say you are following an aircraft, there is one big fat target. It will hit and then the signal will come back. Whereas in particle like raindrop, it's not one raindrop, it's a bunch of raindrops. It's like you can shoot an animal that's coming at you, like a tiger or something. Imagine us trying to shoot mosquitoes. You can kill one mosquito. So it's a much challenging problem. So you need to estimate how many mosquitoes are there. So it's something like that. So radar is a collection of terms. It comes from radio detection and ranging. This is all too fundamental, but I want to be respectful to people who are learning radar for the first time. And that's why I put that in. So the basic principle of the radar is fairly straightforward. So you send a signal and then it hits the target. And then it is like I am taking a ball and I am hitting it to the wall and the ball is coming back. And then I go further and then I hit the ball and the ball will come back after some time. Just by how long the ball takes to come back, I make an estimate of the distance between me and the wall. It's very simple. That principle is being used in radar, except this ball it moves at human speed. The reason I'm using ball is now everybody is in this cricket season, so you can guess the speed and then how long it takes and so on and so forth. And in fact, sometimes people make they look at the trajectory and then from the batsman how far is the distance to the boundary in cricket. Who knows the distance here from the batsman? How long is the distance to the boundary? Yeah, can you get up and speak very loud? 63 to 70 what meters? Anybody, you agree with him? Depends on the ground. 65. Okay, he says 65 meters. So 55. So we can settle this during lunch break. So this will be one of the homework. I'm not joking. We need to have some simple problems to engage people and then do a simple math and then it goes up and down as a 45-degree triangle, the ball. Of course, you can draw the equation of a parabola and get too sophisticated. So you can guess how long the ball takes to reach the boundary. Okay? And I will randomly come and ask you. And then you can guess the speed of the ball. Anyway, so radar signals are like that. For us, it's a very hot season for cricket now. So that's why we are discussing this. So the radar signal is this electromagnetic waves go, hit the targets and come back. So from the distance, from the time difference, which is in electronic time scale, we can determine the range. All this technology was figured out by military. So our community didn't have to invest in developing the technology, but we're using the same technology to look at raindrops. So the main problem with radar is when you have an airplane, many times you're dealing with one or two airplanes, unless it's a massive attack with hundreds of airplanes coming. Okay, which is very different from looking at rain. If you want to many times look at rain, the waves have to go through rain to find rain. You won't find a single raindrop sitting by itself unless it's produced in a lab that like I showed you during the opening session. So this makes the problem very different from weather radars and looking at targets like airplanes. And so that's that. So what it is if you look at, there is another industry from which our community benefited a lot, which made a huge silent revolution in radars that was made possible in the last 15 years, unlike more than 15 years ago. Radars were very expensive. Can you guess which industry we are benefiting from? First, I said military. Military invented radars, so we are benefiting from that. Then there is second industry, that the other industry is developing all the technology, but weather radar community is benefiting from that. Who can guess an answer to that? Aviation, no. Semiconductor is too general an answer. Who? I thought I heard the right answer. Communication, this technology. You must have seen how revolutionary this has been, because this this has more power than some of the computers I used when I joined the graduate school. And more importantly, this can pick up signals very, very weak, and this can communicate with towers and so on. So all the received signals from weather radar are very weak, and lot of the communication technology developed the advances, and we benefited from this, basically comm technology. So they developed the chips, they developed the modern receivers, they developed all the processors. And then an example of something that our own community developed, because it's only we have the need. Can somebody give some example? Take, for example, disdrometers. Have you heard of disdrometers? You have? Can somebody describe what a disdrometer is? You? Yeah, that's true. It's a ground instrument to measure distribution of raindrops that nobody other than our community needs. I think we need a floating wireless mic so that when I engage the audience, he's bringing. Okay, good. We probably need two, because one for this side, one for this side. You sit in the middle, then. So, good. So that's the thing. And where we benefited a lot from other industries. So, one of the things we need to understand is propagating medium, because you have to go through rain to see rain. So, we need to understand how the propagating medium is, and we need to understand that. Okay. So, you see here, there is rain. To see this part of rain, the electromagnetic waves have to go through rain. So, there are two fundamental business of radars. In the old days, I mean, I say old days, 50s and 60s, radars were primarily used for detection purposes. Detect, even in military, used to detect an aircraft. Okay. So a lot of the military work is in the process of detection. I'm overgeneralizing it, but in meteorology, this is all measurement. We need to measure the scattering volume characteristics. Scattering volume is rainfall. Okay? And we need to understand the volume of rain, how heavy it is, and is it rain or is it hail? We have to see. So, anybody from here from a region where it hails a lot? Anybody here from Bihar, Bengal? Have you seen hail? Good. Well, I don't know if hail is good, but you have actually seen. So sometimes hail will produce a lot of backscatter in the in that goes into the radars. So there is also somebody came from Jammu, Kashmir. So you see snow. So does it still snow in Shimla? So because of climate change, I have to keep asking. And so snow also it's not water rain, it's not water particles, and then it's ice particles. What's the fundamental distinction between both are ice, right? Hail is ice, snow is ice. What's the difference? Basic difference? More than shape. Sorry? Fa- Phase? PHASE, phase? Like both are ice phase. Oh, somebody wants to answer in the back. Sorry? Yeah, but that's you're all getting very complicated. But something I'm looking for something simple. Density is also complicated. Do you get hurt if snow falls on you? But if hail falls on you, it get hurt because it comes with high speed. The fall speed is very high, whereas snow falls slowly. That all romantic movies they bring snow into picture, and so the fall speed it is light and flaky, and it's then w- subsequently the reason is he did talk about phase. It's got a lot of air filled in it, particles, and it's water from a hydrology perspective. Its water content is very less. And of course, somebody did mention density. That's all true. So these are all things that we know that we want to be able to be seen with radar, but we want to look at measurement. So the things that we took directly from military technology is the range to the target. That technology we took directly from military, and then the direction of the target is the direction where the antenna is looking, and that technology also we took it directly from military. Nothing had to be reinvented. And then the intensity, the size and dielectric properties of the target that we had to adapt to meteorology. And then velocity, velocity itself we borrowed it from military technology. The basic principle of velocity comes from law of physics. I think I was told that many of you are PhD students in physics, right? Anybody who's physics degree holder here? You raised your hand. So, what's the principle in physics to look at velocity? Doppler. Yes, Doppler is the name of a person. So, one thing that really bothers me when I receive paper or reports is please use capital D for Doppler. Is the name of a person. So, it's called Doppler shift. It's the same thing. It should be obvious these days because now so many stations, Vande Bharat trains don't stop. So they make a horn sound while they cross the station. So you will hear different frequencies when train approaches you and then the train recedes you. The frequency will be higher when the train approaches you and there is making sound. And then and when it recedes, the frequency will be lower. And that's essentially because of Doppler shift. And the change in frequency is because of velocity, and that's converted to a measurement. That also we derived from military technology. I'm going to skip this. I'm going to skip this. Another one that all of you are going to encounter is the bandwidth of the radar signal. As soon as you want to put a radar, first thing is everybody around that place where you want to put a radar gets very excited. Oh, I have this, I have that, I have this signal, I have that signal. You cannot interfere. Radar occupies very, very, very small bandwidth. Radar transmitters, they don't occupy too much bandwidth. It's about the central frequency is about 9 gigahertz for X band. This is thing you will have to worry about. If it's S band, it is done by central government. Central government is very powerful. They will put the radar, and if anybody complains, I'm putting my radar here. Any questions? No. That's how you do, right? See, look at him. He is the IMD representative. He has a radar right in, I can't remember where. And then you have a radar also in C band. In what's the name of the place? I've come to your. Yeah, in Andheri. Andheri is a highly populated place, right? He put a radar. I'm putting a radar, C band radar at 5 gigahertz. This is where it's going. Any questions? Nobody will open their mouth because he is very powerful. Nah, I'm just joking. The X band radar you put here, there. So many people, because like they are small looking radars and they don't look big. They look smaller than the water tank in the top of the building. They will all think you are putting a water tank, but somebody is actually building a radar. So they will ask, what's going on? So, but everybody says, oh, I have this communicating device, I have this wireless tower, I have this, I have that. If you are interfering with them, they are illegally sitting somewhere else. So they are at illegal real estate because radars should occupy very low bandwidth. And this has become a big issue when they make cheap components, and the cheap components, they produce out of band harmonics, and then they interfere, and then all sorts of issues. In fact, I've been working with ARPA for a long time to study this issue and so on. So 9 out of 10 times, if there is an interference with radar and some communicating device, the communicating device is doing something wrong. They are sitting in illegal encroachment land. It's time to take it back. So that the reason I showed this, the bandwidth, the frequency may be carrier frequency may be 9 gigahertz, but the bandwidth is approximately of the order of few megahertz. And few megahertz is so small compared to gigahertz. Giga, everybody understands giga, right? Here, giga is what? 10 to the 9. Mega is 10 to the 6. Good. So it's 1000, factor of 1000 different. Then radars have formed their own coordinate system. Okay. And so are you two in class or are you technical staff? You are in class or technical staff? Class, please come forward because I have been watching. You two have been talking to each other for a long time. Come down. I told you I will show my color as a teacher. Come forward. Sit in front. What about all those people there? You are all class or technical? Half? Last row. What about the people in those two in front? You are in class? Please come forward because I cannot see you. So radar has taken it upon itself to form different coordinate system. This is very common in satellite station things and so on. All angles are measured with respect to local north, and then the elevation angle is measured with respect to local ground. Okay, so the local, anything that's going from the local ground is an elevation, and then if which direction, where is, I don't want to open my phone. Where is north here? Somebody has an iPhone, you can check. This is north. So this is 0 azimuth. Then if I go directly this way, that's 90 degrees. Directly this way is 180 degrees. That's how the coordinate system is. So from now on, I will refer to people as, hey, you at 45-degree azimuth. And you are, no, that's 270, 285, this group. Okay. And then you are like 350, this group of people, 350 degrees azimuth. You are at 10 degrees, plus 10, right? This is north. So you are at plus 10. Are you with me? I'm just trying to make sure. So, so many times you see this PPI displays, and people who are meteorologists have that thing in their head. But people who are coming to this field for the first time, they're like, this display doesn't make sense. Why is north there? Why is south here? Because this is different from the spherical polar coordinate system that's used in physics. If you are a physics master or PhD student, in spherical polar coordinate system, theta angles, theta is goes north directly up and then goes uh, 0 degrees, 90, and then plus 180, and then there is a phi angle. Phi is with respect to whatever the x-axis was. So the radar coordinate system is different from the standard spherical polar coordinate system in physics. This is something I hear. Who's hearing this coordinate system for the first time? Anybody? The radar coordinate. Yes, you find it different from the standard physics, right? Okay. And then the second way the radar does scan is vertical. This is something very important to understand why we scan in the vertical. I want you to sort of imagine how tall, when previous time, Panditharai showed some vertical storms up to what, 17, 18 kilometers. I showed storms up to 18 kilometers. They are considered very tall. Okay. Now, horizontally, how big can be the storms? Can somebody throw me a number? How much? 60 kilometers. He says 60 to 80. We need more numbers. I'm going to check something. Wait. There are storms bigger than 80 kilometers horizontally. Yeah. More than 100 kilometers. Somebody wants to go more than 100? Doesn't matter. Storms. 200. Few hundred kilometers. No, I'm talking about how big can you go? I heard some big number here.
1,000 kilometer it can go, like
1,000 kilometers.
unmixed 2,000.
Which storms? Sorry? Mid latitude or cyclones.
Yes.
You can have a cyclone that's 1,000 kilometer wide. So if you think about it, hey, this is good. I can speak from here. I can really keep a watch on everybody. So if you can talk about 1,000 kilometer storm, and even the 1,000 kilometer storm, the height is only uh, 18 kilometers. So if you close your eyes and imagine, that's a very thin layer. Okay? It's so thin. So many times, everything that happens over hundreds of kilometers in the horizontal happens in all about 15 kilometers in the vertical. Right? So, which means vertical structure is very important. And many times, when the storm pictures are shown in vertical, the vertical part is always stretched disproportionately. You will find that people who are first time coming into the field, they find it a little weird because the scale of the x-axis and the scale, even in this picture I have shown here, wow, this laser is powerful. Even this picture I have shown here, I can't read it myself, so I have to go there. The vertical is about 14 kilometers, whereas the horizontal is it's about 60 kilometers this way. 0, 60, 80, 100, 120. Oh, it's 150 kilometers this way. And this is only 15 kilometers. So it's heavily expanded in the vertical direction. It's by a factor of 10. This will be very typical when you see vertical cut picture of storms. People who are used to be in the field, they just take it for granted. The newcomers will find it very complicated. Okay, let's keep moving. So it's a very simple law of physics. The distance to the target is 2 r over c. That is the time, because it has to make a round trip. If the r is the distance, twice the distance and back, it's moving at velocity of light. So if r is in the order of 100 kilometers or 150 kilometers, 2r is 300 kilometers, and then divide by c, which is, everybody remember c? Somebody give me a number. Right, 3 times 10 to the 8 or 10 to the 10, depending on unit you use. I just want to make sure you know your basic physics. And then you take the ratio, you will get so many numbers, you will get 1 millisecond. So make sure, the one thing you will find in radars is there will be a lot of 10 to the plus 6, 10 to the minus 8. That 10 to the power, you have to keep it straight. Otherwise, you'll get your units very wrong. So in fact, we have an example of in the recitation, radar calibration. You will be dealing with numbers 10 to the plus 8, 10 to the minus 20 everywhere. And you get something wrong, everything will go wrong. So from which you can get the distance r. I'm going to, it's not moving. Okay. So then there is this, I'm again going through all the basics here. Maximum unambiguous range. So this is a very fundamental concept with not only weather radars, it's also an important concept with military radar. The way the radar works about finding the distance to a object is, you know, when you send the signal, okay, and then it's coming back after being scattered from the target. So you take the difference between when you sent and when it's coming back, and then you make the get an idea of how far the target is. But once you determine that everybody who you have sent has come back, you send the next signal. Sometimes this happens, it has happened to me in Indian Railways. Sometimes the trains are so late. I used to travel very regularly from Calcutta to Madras. It's a 30 to 46 hour train ride. At any given time, there is a train going from Calcutta to Madras. Sometimes, when the train becomes too late, and then you see the train arriving in Madras, sometimes people will ask, is this today's train or yesterday's train? I'm sure you have heard this, right? So we have the same problem. This is ambiguity. Sometimes when the target is very far, then it takes a long time for the signal that you sent to hit the target and come back. And then you think everything has come back, but then you send the next pulse. The next pulse hits another target very close by and comes back. They both come at the same time. Whereas once you have sent the next pulse, you forget about all the previous pulses. So then you will get into this ambiguity. Is it this pulse's return or the previous pulse's return? Which is same as the ambiguity of is this today's train or yesterday's train? So you have to resolve that. There are so many, this is all old days issue, but nowadays there is so much technology. Nobody even talks about it. It's all been solved by technology. So this is how it happens. You send one pulse. And also I wanted to slowly start throwing numbers. This is one way I'm going to say a lot of things without going through them formally because you have to catch up because these things are taught over 2 semesters. How can we talk about that in 3 days? So you send a pulse, okay? Then you send the next pulse. These things are sent at electronic time scales. Typically, the time between one pulse and the next pulse in a standard weather radar, it's in the order of, can somebody give me an answer? Somebody who's in the field? It's in the order of 1 millisecond. 1 millisecond is very small. And so that's all it takes if you're moving at velocity of light to go to some big distances and come back. And then you then send the next pulse and the next pulse, and then you keep on getting returns, and then you work with it. That's how a radar operates. Sometimes, if you something is going to come from this pulse after a long time, then that's coming from a very far away target, which means a big hailstorm. That is like Calcutta radar looking at some storms over, I don't know, Jharkhand. Is that far enough? I don't know. I can't remember the Jharkhand. All these states were divided up after I left. So from here, how far do you see for second trip for using Mumbai radar? You'll see up to Satara. Yeah. Anybody knows how far is Satara from Mumbai? How much time by train? 8 hours? 200 kilometers is too close. 700. You see, now we will settle this during lunch. Good. So, if you decide I have to see up to 300 kilometers or 150 kilometers, then you can decide how frequently am I going to send pulses. One way to identify is you color code the pulse. It's just joking here. This coding is done electronically. It's the same way coding is done from different people talking in the cell phones. And then you can determine which pulse sent what. Okay, radars. Here, most of the radars we are talking about is weather radars, but there are people here who work with cloud radars, and then you cannot these radars. Anybody who has seen them, they are very big. You cannot put them into space or mobile platforms. You can keep on miniaturizing radars. Many people have. I don't know who has that kind of equipment here. I bet somebody here is driving around with a radar. There are cars that now will give you warning with backup radars. So those are all very small radars. And So you can think of radars as between 100 megahertz to 100 gigahertz. Okay. But these are not hard limits. And I'm not going to go through this. But most of the radars we talk about are in the SC and X band. S band is what has been historically has been there with all the IMD radars in Chennai, Calcutta, Delhi, many places, and then it took a long time for um, IMD to warm up to C band, and it worked. And then all this moving to higher frequencies happened because of polarization. That's one thing you have to remember. Okay, so the receiver processor, where all the radars have gone through a silent revolution. All the technology that's available in all this, there is a lot of receiver processor technologies that have been made available to the weather radars. So we have all benefited a lot in the receiver and processor technology. The transmitter technology, we benefited from military. So finally, we put together and we make good radars. Okay, this is the distribution of radars in the US. You can see there are about 150 radars. And I got this from, I don't know where I should click. This is the current India radar network. I got this from IMD. So if you don't like this, don't blame me. Which place are you from? Oh, you're from Pune. Anybody else from IMD? Yes. Which place? Mumbai. Oh, same office as him. Pune? Mumbai. Sorry, you have to speak up. I can't hear. IMD Pune, but somebody from far away. Let me see. Patiala. Wow. Great. So you also qualify as coming a long way. You didn't say anything. Well, once he said Jammu, he killed everybody in competition. I was looking for somebody from Northeast. Oh, you're from Northeast? I can't hear you. So,
Hello,
yeah.
I'm from Assam, Northeast, but I'm doing my master's here in Pune University.
Oh, okay. So you are both. So this is the current India radar network. So come on. The laser works. I guess the clicker doesn't. Let me go there. I have a picture of the future India network also. And this is the future network. The I put 22x because I don't know when it will be done. And you can see clearly it's a lot more dense. And it's got two colors, planned DWRs, that is yellow, and existing. So you heard all the VIPs speak this morning. People were talking numbers like hundreds of radars, right? So that's a large number of radars, but those are only big radars. But as city governments and state governments start putting network of X-band radars, then that number will just explode. And one good thing about India is interstate competition. If one state has it, then other state will want it, and then like as soon as Mumbai network becomes popular, all other states would want it. So, and the thing is, in the old days, the big national network was the amount of funding needed was in the order of parliament style funding. But now the cost of these things have come down so much that city corporations can afford to buy these networks. It's you don't need that level of funding. So that alone will change the landscape. Okay. Now, this is a very important topic. If X-band radars were so cheap, why weren't they built before? Right? So that's the question you have to ask. Because a lot of the youngsters who are actually doing studies or I get thesis from, they just don't have a clue. Oh, X-band radars are cheap, so we are building X-band radars and deploying. If it is whereas all other IMD has only S and C-band radars. Of course, IMD will buy cheap radars if they could have bought it cheap. X-band radars didn't exist before. In military, it existed, but for weather applications, it didn't exist before. Why? Somebody should ask that question. Anybody here has an answer? Sorry. Yes, the same problem that is used to virtually almost everybody has microwave at home these days, right? Anything that has water content, microwave can heat it up, and that water is also absorbs waves. So the problem is not attenuation. We receive satellite dish TVs now, and those are at K band. We still receive signals, but you need to provide some extra signal to get all this, because even if the signal is weak, so long you see something, we know how to pull it up, because we know how to deal with weak signals with these cell phones. One person's cell phone doesn't interfere with the other unless the person is talking loudly. So it's only acoustic interference, not electromagnetic interference. So previously, we didn't even know how much attenuation is there, how weak it is, and then we needed to quantify that attenuation, and that had to be taken out. And the way to quantify attenuation was enabled through dual polarization. That's the most important. The dual polarization had to be discovered. And then the US government sanctioned a big project. Just like for K band, all satellites, when you design links, we need design curves for each region of the globe. How much extra attenuation you have to account for if you have to communicate at K band. So for that, I remember we were part of that project. There was a program called TechSat, where there was a beacon at K band throughout the world. Therefore, there were different receivers, and we monitored the attenuation statistics, and then we reported. So we want to make sure that 90% of the time. So if you are transmitting to Mumbai, then during monsoon season, you need to put out a lot of power because it's raining all the time. So the signal will come. So we need that background information. So that type of design systems were not available. So US government sanctioned a big project called CASA to figure this out. That is how we can build small network of radars. And also that's the first thing. Second thing is, if you have to account for attenuation, you need to build, let's say attenuation is additional 10 dB. You need to come up with 10 dB more power. 10 dB is a factor of 10. 10 dB more power means you go from 1 kilowatt transmitter to 10 kilowatt. You put 20 dB more power, that's 100 kilowatts. Suddenly your transmitter starts looking like a nuclear reactor, a lot of power. Sometimes it's much, because X-band systems are so small, it's cheaper to put another radar nearby instead of having to see a long path. There's no need to see the long path, which is the same principle under which the cell phone operates. from your cell phone, if you don't get signal, what is the term you use to describe that? It's actually very good. In India, it's very technical. Now, network is poor is that's different problem. If you don't even see a signal, no range or no tower. I've seen so many people say I cannot find tower. I've heard that, which means all that you have to do is communicate to the closest tower. Once you get to the tower, then you can go anywhere. Same thing. So if you have cheap X-band radars, you can put a whole bunch of them. That's what was shown in the TV show, right? That guy explained it much simpler and better than me. That's why the TV people are in the communicating business. So you can build many radars and then network them. And that's the project that is being done at Mumbai. So what's the distance between two radars in Mumbai? The farthest? 30 kilometers, you see? Whereas 30 kilometers is called very close in Rajeshwar Rao, right? Rajshekhar Rao, sorry. See, I got 90% of it right. um, uh, his radar, 30 kilometers is like right here, right in front of the radar for him. So, whereas that's distance between radars. Whereas for you, distance between two radars is out of state, almost. So, that's the main issue. So, you need to take care of absorption. Absorption is very dominant up to frequencies up to 14 gigahertz. That's physics. So, the cause of attenuation in the precipitating atmosphere is absorption. So, which is you see water particles. So, if I have to tighten it a little bit, that is e to the negative jkr, k is the propagation constant. In free space, it's 2 pi over lambda, and then which is 2 pi f over c. These are very basic equations in physics. Do you all know this? Everybody? If you don't know it, you are hearing it for the first time. Again, listen, you're not supposed to learn everything from this. So convince your office, if you want to know all the basic simple equations, convince your office to buy this book or some other book. I'm not trying to sell my book here. I don't get any money out of this. But convince your office to get a book. That's the best way you can look up these simple things. Those guys are going, he's selling book. So the main thing is we all know there is attenuation. The $1,000,000 question is how much is that attenuation? Because the signal coming back is weak. Is the signal coming back weak because we have a weak storm, or there is a strong storm that's being attenuated? If I know exactly how much the attenuation is, you can rebuild the signal and I can tell what is the original reflectivity. Immediately, I am able to use X-band radars. All this technology development, nobody was doing for weather radars. So the US government invested in a big project called CASA to develop all the design curves, design information. Then after the CASA project, everybody started selling X-band radars. That is the main contribution here. So the propagation constant typically is computed as sigma extinction NFDDD. Tomorrow or day after, when do we compute this in the recitation? No, it's okay. We will be able to compute this to get with different rainfall. So historically, people tried to get this attenuation from reflectivity itself. It didn't work. because it was a iteratively building problem and it just blew up. But that was accomplished through what is called as differential propagation phase. I'm not going to go through this in detail. However, you see, so because of this, I'm just showing an example of a C-band radar which was attenuated, and then the whole attenuation was constructed using PDP. Red is corrected for attenuation. See that scale here is 20 dB. You can build back up 20 dB loss of signal correcting for attenuation at C band. If you can do it at C band, then we thought, why don't we do it at X band? And that resulted in the ability to design and deploy small, compact X band radars. And all the design curves were put out by the CASA project, and the industry picked up and then started making X band radars. Before CASA project, there was hardly any X band. You can't even buy it. Those in the radar procurement business will understand, right? Let me skip this. So, no, I'm not ending, but this is a place to pause. I have been talking to you for like an hour, right? So I need to slow down a little bit because I teach class. Typically, classes in universities are about 45 to 50 minutes. And the reason they are 45 to 50 minutes is because, not because of the subject content. Somebody has studied. After 50 minutes, they stop listening. You can talk. They will look at you. Their ears will be open. लेकिन अंदर कुछ नहीं चलेगा. So it's what we are going to do is we are going to look at a summary, and then without leaving the room, I have invented a way to take a small break, but we will get to that. I learned this from a lifestyle coach. I'm getting more exercise here. Okay. Attenuation correction can be done using differential propagation phase, and real time, this can all be done in real time. No problem. Processors are so fast now. The reason why you have to do much this, in a weather radar, it sees large number of data. It takes about 1,000 data points along the range. Everything has to be done within 1 millisecond. Not an issue with the modern processors. Computer industry has solved this problem for us. It's not even an issue. And then this makes C-band radars very competitive with S-band. So that's why if you see in the world market, a lot of people are starting to manufacture C-band radars because they can be made much cheaper than S-band. S-band, one of the problem is, you know, what's the biggest, you may not even guess, what's the biggest cost of S-band radar, S as in Sam? I only, people like IMD may be able to answer this question. Why S-band is so expensive? Sorry? Yes. I was talking to some Korean weather radar people. I was telling them C-band radar will cost that much, X-band, S-band radar. They were not even paying attention. Why? Oh, the real estate cost in Korea is so much. Cost of the radar is peanuts. It comes in some rounding error. The real estate finding, I don't know how these people found real estate in Mumbai. I have to check with them, but that's a different story. And so, anyway, we will skip this because I'm going to. So, you look at attenuation margin. if you are seeing up to 100 kilometers, for 95% per 90% performance, you need about 6 to 7 dB more power. You don't need too much more. But I will come back to that. At C band, the same raindrop looks bigger because of the frequency scaling. So naturally, the targets, that's the reason why for cloud radars, people use the W band frequencies or very high frequencies. The same target looks much bigger and returns more signal at higher frequencies. I will show you. So at S band, there is negligible attenuation. It's still few dB. At C band, you need extra, say 80%, 90%, you need additional 6, 7 dB. But the 6, 7 dB is given by the target itself. So nobody argues too much about S versus C band. Okay. Now let's go to X band. X band, there's a lot of attenuation. So using the same statistics we measured over Colorado and Oklahoma, we see the percentage of time the attenuation exceeds. So if you want to see up to ranges of, I want to build radar, X-band radars that look only over the city, which is about 40 kilometers is what we decided for. So that's the green curve. And it's enough if I build in extra 15 dB of attenuation margin. So compared to a standard transmitter, if you have a transmitter that can transmit 15 more dB, it can tackle 15 more dB of attenuation, which will happen 90%. If you do that, 95% of the time, you're without any issue. These are all called design curves. So we generated these design curves as part of the CASA project and put it out to the industry to start making radars. So, come on. Okay. At this point, let's take a small break. Everybody just get up and twist like this. Or if you don't want to get up, do something else. But take a minute to stand up. You'll feel good. Don't leave the building. Don't leave your seat, otherwise it will be very hard to get you back. He is protesting.
No. It will show that we are for yeah. Our Shahrukh Khan does it very Bollywood style.
Sorry?
In a Bollywood style.
Yeah, Bollywood style. You can twist. Maybe I should put some music.
Raindrop.
Raindrop music, yes. You can also ask me questions during the standing break if you want to. Are you having fun?
So how many
It's
radars US has?
we?
Not you. US.
It's very hard to count because it's like showing up everywhere. And it's not
Numbers.
it's not regulated by one. It's like S band. You can regulate by one agency.
So
It's probably hundreds, several hundreds.
owned by
different, no, not just different, like municipalities. Yeah, no, municipalities. Mm. Huh. I don't have slides here, but I will show you. There are some places I'm running a project in California. We have 3 S-band radars, but still that won't do the job because a lot of mountain ranges and it rains very heavily in the valley. None of the X-band can see, but with the 4 X-band and 1 C-band, we are able to. We are going to cover same as 3 S-band region, but it's a very specific situation. We do use the S-band too because it's already paid for and it's already there. It's not. I'm not trying to say S-band is useless. This is augmented very easily because it's already paid for and it's already there. No, this is actually in the coastal region in California, but it's like Kerala type situation where there is mountain range and then there is other mountain range. In between there is a big valley. And that valley is very high value valley. So towards C, we are putting the C band to C, and you can use S band in the coastal regions. Yes. Mhm. Okay. Are we stretched enough? Actually, I even had a better idea. I was going to say you can swap seats with your neighbor, but that gets too controversial. I said, I came early to catch the best seat. I don't want to give up my seat. It's like in a plane. Okay. My God. Minimum detectable signal. Anybody who has been working on the tender to buy radars, most of the times, whenever you see S band manufacturers, they will be offering 1 megawatt peak transmitter, right? Whereas you look at C band, most of them will offer 250 kilowatt transmitter, right? You should wonder why. Because I want to show you an equation for minimum detectable signal. I think in our recitation today, we have a program to play with this, right? Today's recitation. So we have this equation that we actually will give problems today. So there is P0, which is the pulse width of the radar, transmit power, gain, lambda. So many things are there in the radar equation. In the next, they have asked me to speak up to 130 to 145 to balance the crowd at the lunchtime. So I'm just, in case you are wondering how long I'm going to talk, you are with me for another 45 minutes. So in the next 45 minutes, I will try to derive this equation for 1 raindrop. Okay. Now, these are the key things that you need to look that changes between S band and the C band. Here, I am showing the minimum detectable signal as a function of range in terms of dBz. dBz is reflectivity. For people who don't deal with the weather radar every day, 25 to 30 dBz is the type of rain Indians don't even think of it as rain. Ah, and you're not going to get wet in this. Let's go. A few drops here, few drops there, you will reach the metro station. No problem. Nobody should call me. Okay? And unless you're all dressed up with a new suit and makeup going for a wedding, then 30 dBz you won't go. It's one drop in the cheeks, the makeup will drift. 40 dBz. You're a young guy like him. He won't stop. Let's go. कुछ नहीं होगा. 40 dBz, I won't go out. I will get wet. 50 dBz, you cannot even see where you are going. And then a bus will go by and splash all the water on you. So, just to give you an idea of the type of rain that you see. So, the minimum detectable dBz minus 40 and all that stuff is nothing is happening. Okay. It's all getting into the cloud range. You should really worry. So, these radars can see quite a bit. S and C band radars. But the S band, for them to be exactly equal, S band is 1 megawatt transmitter, C band is 250 kilowatt transmitter. The reason is there is a lambda square advantage in the minimum detectable signal. The same scatterer is able to produce a better signal at higher frequency. Okay? That's one way to think about it in your mental mapping. When these things can be, and also I will show you an example that take two radars. Chill radar is CSU's our radar. Peak power 1 megawatt transmitter, and antenna diameter is about 9 meters, 8.5 meters, 1 degree beam width. King City radar with Canada, I don't know if the radar still runs. Its peak power is 250 kilowatts, and it's got an antenna diameter which is only 6 meters, much smaller than my 9 meters. But because it's C band, that produces almost 0.6 degree beam width, which was much more sharp, which means has higher gain. And we both have similar noise level floor. Actually, we use slightly more mumbo jumbo to get additional 3 dB. So the processor technology is almost the same, but the King City radar is about 10 dB more sensitive than our radar. They produce 1/4 of the power and they have a smaller antenna. Only because who complete the sentence? It's a lambda square effect are there in C band. So, as far as I'm concerned, if you can buy 2 C band radars for the price of 1 S band, even in the coastal region, I will put 2 C band radars between 2 states, between 2 cities. S band is, it's main reason we want to stay in S band is we want to hold on to that frequency. You give up that frequency, enough people are willing to move in there, especially communication industry. So that's why you don't want to give up S band. Otherwise, anyway, you can complete that sentence. Yes. That the managing the noise floor is not too much so long you manage your bandwidth. It's not a big issue because a lot of the noise floor comes from the front end thing. You have a good LNA and then manage your IF frequency bandwidth low. Those are the only two touch points. You can manage the noise floor fairly well. So it's, yeah, but not to the point of the 10 dB here. If that's an issue, weather service radars, they can easily swap LNA. Their budget is so good that swapping LNA is For you in the university, it's a problem. Yeah.
If you take the range resolution as 150 meter, it is 1 microsecond. So bandwidth is 1 megahertz. So 60 dB we are going there only. So your front end noise figure is around only 1 dB.
Sorry.
According to that noise floor, your front end noise figure is only 1 dB.
But should be more than 1 dB.
But in that case, noise floor will be.
There is some, that's what I said. There is some smoke and mirrors because you can do the, you can dig in below the noise in the A to D with the modern digital IFs.
Yeah.
So that's what I said. We do some mumbo jumbo to pull things up. That's where the noise figure, actually, you can go online and find the number. I think it's about 3 dB something. Even that's a good number. And that's where he's talking about. But I'm glad you have asked the question because he knows what he's talking about. Maybe you can explain this to some others during the break. What I want to do is for the people who are not like him, he's a smart guy, and weather radar equation for a single raindrop. If we understand that, we pretty much understand all the workings of the radar. So this is for all the people who raised their hand and said they are dealing with weather radars for the first time. Okay? So the rest of you, somehow hold on to yourself and say another 40 minutes will be out for lunch. If some reason you want me to finish early, I can finish early also. 1:30 is better? Okay. Enough people have spoken. You see, what is more important than radar meteorology? Lunch. This is a universal factor. Okay. Now you will see me speaking very fast. Consider a pulse Doppler radar transmitting a high frequency sinusoid. Okay. And let's assume the transmitted power PT is sent out by an isotropic antenna. An isotropic antenna sends the energy in all directions. Then the power density at a distance r from the radar is PT divided by 4 pi r square. Where does 4 pi r square come? It's the surface area of a sphere. Okay. And then the unit is watts per meter square. So you take that, and then let's say there is a raindrop sitting at the end of that. Okay. Now, the gain of the system is compared to an isotropic radiator, how much extra you are pushing all in one direction. That's the definition of gain in an antenna. It's a very strange definition of gain compared to gain in an amplifier, but we have to go with that. So the scatterer intercepts a portion of the incident energy and scatters it back in various directions. Okay. Only the power coming back in the direction of the radar is intercepted. Okay. Now, the radar cross section of a single raindrop determines the amount of scattered power. Radar cross section is a quantity that's defined historically to quantify this. So, the concept of radar cross section, when an object is large compared to the wavelength, which is not the case here, the radar cross section of the target is same as the geometric cross section. That is, how much cross section you have to obstruct the energy. That's pi d square if it's large. However, when you have an electric field that's incident on a dielectric sphere, such as a raindrop, then the dipoles in the water molecules, they oscillate and do all sorts of things. That's actually the reason for why your microwave oven works. So the the scattered field is actually proportional to the volume of the sphere, which is d cube, and the power scattered is proportional to v square, which is d to the 6. That's like a simple-handed explanation for where the d to the 6 comes from. I think we need to put the laptop somewhere here so I can. But the true radar cross section, if the scatter is small compared to lambda, lambda for S band 3 gigahertz. So for somebody from who is learning radar for the first time, what is 3 gigahertz lambda compared? Is what is it in centimeters? 10 centimeters. Raindrops in the order of size a few millimeters, so it's much smaller. So the definition, the assumption is very small is valid. So this is the radar cross section of a single raindrop, approximately. So this factor comes from the dielectric factor, whereas k to the 4 comes from what is called as plane wave scattering. The dielectric factor is really responsible for understanding a lot of the microphysics and meteorology, which will be talked about later in the class. When you substitute that back, you will get volume of a sphere is pi 6 d cube. K0 is 2 pi over lambda. So sigma is pi to the 5 divided by lambda to the 4 k square times d to the 6. What is k? Is this factor epsilon r minus 1 divided by epsilon r plus 2. What is epsilon r? For the people who are in physics curriculum here, I'm just using the term epsilon r, but do you know what that is? I'm going to come down. It's dielectric constant, right? And dielectric constant, relative permittivity. Yes, that's also the right answer. And that dielectric constant of water is a function of frequency that will play a role. And also the dielectric constant is complex, which makes water attenuating. So what is the radar cross section? The radar cross section is defined as an area such that if the incident power density, when it's intercepted by this area, then when that backscatters as an isotropic radiator, it produces the same power. It's like a concept. So the power density coming back to the radar from a single raindrop is PTG divided by 4 pi r square times sigma divided by 4 pi r square. I'm spending more time clicking here. We need to fix this. Is this the clickers? There's a rat's nest here. What's going through this? Let's see if this works. It didn't help. Something is stuck. I need this. This clicker is not. Hmm? So the power received in watts is PTGT over 4 pi r square, sigma divided by 4 pi r square, and the received signal is intercepted by the antenna, that's AE. So when you put all these together, the power received in watts from one raindrop is lambda square PTG square sigma divided by 4 pi cube r to the 4. I know it's a little fast before lunch for people who are seeing it for the first time. See some few things. The power drops off as r to the 4 from single raindrop. That's a sharp drop. And it goes up as lambda square, and it's g square because g is the gain of the antenna. That gain is multiplied twice, one for transmit, once for receive. So the corresponding voltage is everything square root. So we can get that. So the term e to the negative j 2kr comes from the two-way propagating wave. And now you will never find a single raindrop by itself. It will be sitting in groups. Click, click, click. Oh. Let me see. Put this down. Let me elevate this and put it on something. It's not, this is the clicker, right?
No, no, no. You accidentally click this one. This is a mouse. You have to click only this.
No, no, I'm clicking this. Okay. It's not having a range properly. Anyway, so all the raindrops together in a volume is coming together. How that happens? This is a little complex diagram. I will probably explain this after lunch. It's not a good topic if you're learning it for the first time to learn it before lunch. Okay. One way to think about this is it's, it's new. Okay. I blamed it on the clicker. He just gave me a new one. So when you go far away in the radar beam, there are more raindrops. How much is there? R theta is the length of the arc. So the volume there is delta R, that's the range, is CT0 over 2 multiplied by, let me skip all this. You see this volume? This volume increases as R square, R theta times R theta. So R square theta square. So you add up all the power from all the raindrops, that will go up as R square. And this is a tough slide to go through between you and your lunch. So what it is I am taking the antenna pattern and integrating all the raindrops inside and then adding up the power. Are you able to conceptualize it? The actual math is not a good thing to do before lunch. After lunch also is not good, but after tea break is good. So you can see that's why suddenly there is a lot of math here. You see there is a disk and the disk gets bigger as we go further. So when you want to simplify things, you assume it's integral. You assume a Gaussian pattern for the antenna pattern. You do all that. And then when you integrate the antenna pattern, you get pi theta 1 C1 divided by 8 natural log of 2. Trust me, this works. So when then individual raindrop, the scatter cross section is this. So you put it all together, the equivalent reflectivity is lambda to the 4 pi to the 5 kW square times eta. Eta is the volumetric radar cross section. Radar cross section has the unit of meter square. So, and you have so many meter square radar cross section in a unit volume. So you put it as so many meter square per meter cube. So you put that all in, you get this, which is radar equation. Yes. Yeah. Yes. You basically just integrate the pattern and you will come up with a number. And even if it's phased array, the one assumption to make is if you go off axis, within that thing, it's still Gaussian, except that theta and phi, you just, typically what you do, if I am asked to find the average height of people in Pune, I'm too lazy. What I'm going to do is I'm going to ask you all to stand up and find the height of all of you, and then fit a Gaussian, and then declare this is the average height of people in Pune. And similar to that, whatever data you have, even if it's off axis, the whatever curve you have, put a force fit a Gaussian, and then the theta and phi will change. So you change that instead of changing the Gaussian assumption. The reason is you make a Gaussian assumption and take the integral, and then you integrate the actual pattern. The error will be so negligible compared to all the other errors you are making. Actually, you need to get a microphone so that other people also can. Can you somebody give him a mic? Can you comprehensively explain your question? I understood the question quickly, but if you have to explain to, let's take someone. You know phased array radars? You know? Oh, who doesn't know phased array? You know? Good. She needs to understand. Explain to her that way.
So, okay. So the equation which Professor Chandra explained, the triple integral of f squared is equal to pi theta 1 phi 1 8 ln of 2. That is for a Gaussian beam shape. That is true when you are using an antenna, which is the normal radar which you use here. But let's say you are using a phased array radar. Phased array radar, it has an antenna and it doesn't rotate. I mean, there are various techniques which are used, but let's say if you use electronic scanning, then you use the phase change between the inputs to direct the beam at different angles. So if it is at the broad side, it is fine, same as what we see here. But if it is off broad side, the Gaussian shape may not hold. So that is what I was asking Professor Chandra as to what to do if the Gaussian shape doesn't hold for phased array radar. And that is what we also did something similar, but he also said the same answer, so it worked.
Okay. You got it? No. What he's saying is if you go where, you see, you take a reflector antenna and then you scan like this. Okay. Which means and I should be away from here. Which means the antenna doesn't change. So if you are looking this way or looking this way, it's the same antenna pattern. That is, the beam has same 1 degree. But you are not allowed to turn like this and turn like this and scan. Okay. Instead, I should look like this. When I want to look at you, I should look like this. When I want to look at him, I should look like this. So that is scanning. And when I look like this, my visibility changes. In fact, I go through a eye test during every time I have to for my annual. That peripheral vision is a little tricky. It's important as a driver. You should have, like they say, parents have the ears in the back of their eyes, I mean, head. So that vision. So what you do is, he is asking how to adjust for Gaussian. First of all, the pattern will not look Gaussian and it may look fatter. But what you do is you force fit the Gaussian, but the net result will be the theta and phi, which is the beam widths, will become different. So if you are here, the beam width will be a little fatter. Whereas if you're here, it will be another beam width, it will be here another beam width. So we actually calibrate that in a phased array, and we take care of that in the radar constant. So it's a very detailed question. Okay. So this is the final radar equation. Power received is proportional to the pulse width you transmit, the velocity of light, transmitted power, gain of the antenna, and then the beam width of the antenna, reflectivity, how far it is, and this is the dielectric. It depends on so many things by the time you get your DBZ. And then Professor Somendra wants to convert, after coming through all this, he wants a simple formula GR and he wants to convert it to rainfall. So we have to make a good connection. Otherwise, we just randomly do something, we lose. So here is the sensitivity. You will find these sensitivities are extremely sensitive from weather radars. So we can see insects flying from 100 kilometers away. These weather radars are very sensitive. So where is, oh, there he is. Have you seen, do you even have a grasshopper season here? Have you seen insects with your radar and far away? You need in rural region. Yes. Okay. In Bhopal, you've seen? Yeah. So in fact, those are used as tracer for wind. And so when you tell people, I am seeing locusts 70, 80 kilometers away with my radar, they won't even believe. And I've actually done lots of experiments. People have run with a net and caught insects and found number density and tried to calculate reflectivity. Actually, I have a, in the latest IRAT proceeding that is still to come out from IIT Indore, there was a IRAT, right? So I wrote a paper on birds and insects. So it's to document that. So that's for you. I've got a lot of details here. So you can see the minimum detectable signal. So the radar can see a few raindrops from very, very far away, which is, you'll be amazed to see how sensitive the weather radars are. I'm being too hopeful from. Okay. Resolution. Resolution of the radar is very fine when you're close to the radar, but the beam widens as you go far away. So it's determined by r theta, which is basic law of geometry. And so because of that, r theta, huh? Two people from there in the back disappeared. I've been tracking them for a while. That's, I really do a good track of mapping here. As I go like this, when I was talking this side and the phased array, they just disappeared. I think they got offended when I asked them to move forward. I will catch them at lunch. You know, in US, we have this multiple movie theaters in the same complex. I don't know if you have that here. So sometimes if one movie is boring, people will leave and quietly go into the next movie. So like that, maybe they are attending the workshop upstairs, modeling. Okay. So you can see this is the disk over which the radar is measuring. So the disk is very thin. That's determined in radial direction by the pulse width. It's about CT0/2, which is for most of the weather radars, it's about 150 meters. And whereas the cross range resolution, the disk gets bigger and bigger as you go far away from the radar. Okay? So that distance at 60 kilometers for 1 degree beam can be as much as, who can tell me the geometry? 1 degree beam, 60 kilometers can be as much as the cross range resolution. How much? It's about 1 kilometer. Okay. That delta R is CT0/2. Range resolution depends on the pulse width, whereas R theta. This is actually a bigger problem for phased array radars. As you go, the reflectivity has to be calibrated off axis. I did talk about this. I just want to introduce dual polarization. I should be ending now. I'm not even close to. I will skip these. I showed this during the overview. So here is more stuff. As I told you, many times, lot of the references you make is radar produces plane waves, but you think it's spherically going out. That's because the local plane, Earth, when you look, it's flat, and really it's a sphere. That's because it's locally flat. So the plane wave is pretty much like that. Very rarely you are too close to the radar. Oops, I don't want to come. So that's how you see a plane wave. And then this is polarization. You have to be careful how you define polarization. Polarization is always defined with respect to the antenna. Most of the times, you are looking with the radar almost horizontally very far. So horizontal polarization is like this, vertical polarization is like this. But sometimes you look up with the antenna and then rotate like this, in which case the horizontal and vertical just come this way. So these are things I wanted you to pay attention to. Then there are circular polarizations. We will skip that. This is okay. This is about systems and technology, X band, C band, and all that stuff. There are so many ways to architecturally do dual polarization radars. You can sometimes in solid state systems, you don't have too much power. So what you do is you use the same transmitter, but it's much easy to switch in solid state compared to high power tubes like magnetron or klystron. So what you do is you transmit one polarization at a time alternatively, and then you also receive one polarization at a time alternatively. If you do that, it's called alternate transmit, alternate receive. You can also do simultaneous transmit, simultaneous receive. If you have a lot of power to transmit and you have money is no object, you have many receivers you can build, then you have that. So our radar is in this category. Alternate transmit, simultaneous receive. So that is, you transmit one polarization, you transmit another polarization, but on receive, you always receive H and V. And then simultaneous transmit, simultaneous receive. So that's another type. So many times when we do PPI at 2 degrees elevation, the antenna is looking like this and we scan. But when you look at the plot, it looks like it's flat because people ignore the 2 degrees. You have to remember, seriously, the scan picture you are getting on the surface of a cone. But the cone is so big, it's almost taken as flat. But when you do very high elevation, please don't forget this. A lot of the times, weather service, they won't go beyond 10 degrees or some 15. And so people are used to making only horizontal pictures. Whereas RHI is a vertical scan. I already talked about that. This is volume definitions. The reason I'm going through these things is when you look at the book, you will see the same figures and you will become familiar. You can see when you are close in, the volume is small. When you are far away, the volume is big. This is one more thing you need to understand, which is the radar is looking up, and as you go far away, the height is measured as local height. So, and this is distance is on a surface of the earth, and there is all sorts of geometry issues come. So when you do simple geometry, it works for up to 50, 60 kilometers. If you go beyond 100, you need to be a little careful. Okay. If you do straight line geometry, then you will drop farther to the surface of the earth. You need to remember that. Are you familiar with what I'm talking about? People who are new? For me, you are the representative of people. You are also new, or you know radars before? Good. Who else is new here? New radar person. Good. Yes. After lunch, I will keep you in the front so I can keep watch on you. I want to finish this. Okay. I'm only 7 minutes behind. Now I'm really winding up. So we talked about electromagnetic propagation. We talked about range, direction, intensity, velocity. We talked about radar as a system. We went from S band, C band, X band. Radar coordinates, radar equation for a single raindrop, weather radar equation, concept of reflectivity, sensitivity, resolution, why dual polarization, lunch. Any burning question before we leave for lunch? Sorry? What's there for lunch? Now I want to know where is lunch. Any quick question? Yes. Who is asking question before? Who? Oh, okay, okay. See, online people are standing between you and your lunch. They may be eating, yes. One? No? Arita, any question? You don't want to ask any pre-lunch question? Oh, Hilan, question? I didn't notice you guys. Otherwise, I would have dragged you to the front. These people have come from Madras. Well, Trivandrum is farther. Okay. Lunch. Thank you.
Lunch is available in the basement. We'll be rejoining back at 2:30. Thank you. Radar variables computation. We welcome you, sir. We won't be able to connect the laptop because this is connected to Teams and everything.
Store it as PDF, save it as PDF, and the PPT will work.
Yeah, yeah. Actually, that laptop actually connects with the MS Teams and the YouTube screen. So,
Okay, then I
let's fix that.
what about the MATLAB session and all?
Just inquire and get back to you. Sessions included with this?
Yeah. MATLAB है इस पे?
I missed this. नहीं है? Okay. I'll get back to you.
हाँ इसमें है डेटा सब है MATLAB का.
Yeah, I'll inform somebody to connect with that. Just give me.
देखिए देखते हैं क्या होता है ये खुलता भी है कि नहीं. हाँ. Sir, my
Hello. So, good afternoon, everyone. I'm Dr. Swarup Sahu. So, even though this is a workshop, some of the things, a few of the slides that I will be presenting is a joint work between CSU and IIT Palakkad. So, I'd like to acknowledge the work that we have done together. So, this is the introduction to spectral polarimetric radar variables. So, as Professor Chandra has given a very uh, elaborate introduction to radars and polarimetric weather radar. So I will take it over from there and explain some of the details. So let's look at what do polarimetric weather radars measure, or what are the radar measurements that we are mostly used to looking at. So, uh, so here is a radar which is radar like a diagram. It's a cartoon which shows the radar resolution volume, which is already discussed in the previous session. Then we have this cartoon where we see precipitation or any kind of distributed target. So there are multiple kinds of targets. I would like to focus, just point out again that we are dealing with distributed volumetric targets. It's not point target like an aircraft. It's a distributed target, volumetric target. And it fills the, most of the times it fills the radar beam. Uh, Sometimes it doesn't, so that leads to different kinds of problems, but most of the times it fills the radar beam. And what do we measure? We measure polarimetric we get polarimetric measurements. Before that, there is radar movements. One is radar reflectivity, which is a measure of the return signal or the backscattered signal towards the radar. Then we have differential reflectivity. Differential reflectivity is the ratio of ratio of horizontal reflectivity over vertical reflectivity. So it's a measure of the shape of the particle. So if the particle is horizontally oriented, or the major axis of the particle is horizontal to the ground or horizontal to the beam, then you will see that differential reflectivity is positive. If the particle is vertically oriented, that is, let's say you take a needle, it's vertically oriented. So similarly, if a particle is vertically oriented, then you will get a negative value. Then there is copolar correlation coefficient. So copolar correlation coefficient is a measure of like similarity between the particles. So similarity in terms of shape, size, distribution. For example, if all the particles are rain and are of similar size, then you will get a value between 0.95 and 1. But if the particles are, if you go to the melting layer where there will be melting particles, some may not be melting, or in the starting of the melting phase, you will see get a value of 0.9 to 0.95 depending on what kind of precipitation it is and all. I mean, where it is and all. Then you have a differential phase and linear depolarization ratio. We'll talk about it later. Uh, so when you use a polarimetric, use these polarimetric measurements in a with a weather radar, you, for each resolution volume, you see this resolution volume, you have one value for each of these uh, resolution volumes. You assign one value, and considering that, you have to think all the variables you are trying to estimate. You are trying to estimate rain rate, you are trying to estimate type of particles, you are trying to estimate the distribution of the particles, you are trying to estimate the size distribution and the phases of the particles. So considering that, it's asking too much. So you're asking too much from these four variables: differential reflectivity, copolar correlation coefficient, differential phase, and linear depolarization ratio. So, so again, so we have polarimetric weather radar. What are the so we have the uh, reflectivity, Doppler velocity, spectral width. Doppler velocity is the mean velocity of all the particles moving in a resolution volume, mean radial velocity. It is weighted by the reflectivity of the resolution volume. Then we have spectral width. It's the variability associated with the Doppler velocity, mean Doppler velocity. Then you have polarimetric variables, which I have already discussed. When you combine polarimetric variables with Doppler information, you get spectral polarimetric variables. When you combine these two, you have the polarimetric variables and the Doppler information, you get the spectral polarimetric variables. You also have the Doppler spectrum, which I will show. On each of the parameters which I'm talking about, I'll show an example to explain. So the Doppler and polarimetric measurements from a weather radar can be used to uh, monitor and track precipitation or the type of particles, the phases of the hydrometeors, and so on. Okay, so what are the spectral polarimetric variables? We have the spectral polarimetry, which combines we have the spectral polarimetry that combines the Doppler and polarimetric information, so that it represents a distribution of the polarimetric variables as a function of the radial velocity. So you have the Doppler variable, which we saw as differential reflectivity. So instead of having one number for one resolution volume, you have this differential reflectivity as a distribution over multiple velocity values. So we'll see that. Then we have Doppler reflectivity spectrum. It is as the distribution of hydrometeors radial velocity weighted by appropriate backscatter cross section. So then there are variety of applications of spectral polarimetry. Let's look at the applications first. Then we understand the importance of this thing. So before we go to the application, what is the difference again? So we have measures polarimetry. As I said, there are four variables. The measures bulk polarimetric variable for one radar resolution volume. And then you have here in spectral polarimetric, you have polarimetric movements as a function of Doppler velocity. Then polarimetry, it's challenging to resolve multiple hydrometeor types, but that can be done using spectral polarimetry, and a lot of research work is going on that uh, that aspect to resolve hydrometeor types. Then polarimetry estimates turbulence and wind shear indirectly. So the wind shear and turbulence is estimated indirectly, but that can be done directly using spectral polarimetric variables, or particularly the spectral spreading, spectral broadening, and spectral differential reflectivity. So what are the various applications? As I said, we'll go over the applications. So first of all, classify noise, clutter, and precipitation for estimation of Doppler and polarimetric moments. So see, some of the work has already been done. So let's look at that first. So what is clutter? Clutter, what is clutter? Can anyone please specify what is clutter? So clutter is basically anything which is not which is not precipitation or anything which we do not want to measure. For example, a mountain would be a clutter. In our case, a mountain would be a clutter. Mountain is a clutter if you are trying to detect an aircraft, and buildings are clutters. Then you have, so you can easily determine what is clutter, and then you can classify noise. Noise is because of various reasons. We'll get to that when you'll see the results, where what is noise. So noise, it could be because some particles move from one radar resolution volume to another one, and that creates a variation in the measurement. So that creates a noisy measurement, and that affects our measurement. So that can also be removed. Then you can filter out biological clutter. So all of this biological clutter, what is biological clutter? Birds or insects. Then you can determine the turbulence intensity in rain using spectral differential reflectivity. You can determine the turbulence. You will see that when there is lot of turbulence, there is a certain uh, characteristic of the differential reflectivity spectrum. You can determine the drop size distribution from Doppler spectrum. Then there is something called size sorting. When the size sorting can be done for vertical wind shear. So look at that. Then the most of the work nowadays is being done for this, that is hydrometeor microphysical properties and processes. So we want to determine what are the microphysical properties that we can extract from spectral polarimetric variables. For example, you can determine whether it is ice particles like crystals, or dendrites, or aggregates, or graupel, or hail. I mean, work is still going on. But it's like we are getting there. Now, what are the well established applications? That is clutter removal from measurements. That is well established. It has been done. It is being done. Then you have shear induced size sorting, that I will get to. Then you have separating hydrometeor types. Broad separation, not exactly the separation for particle to particle, but broad separation can be done. For example, you can look vertically up, and when you are doing the measurements, you can tell whether it is bigger particles or smaller particles. That can be done. Then what is ongoing research? Like broadly, what are the people working on? One is the Hale size distribution. Hale size distribution in convective core, that we are trying to do. Then we have ice aggregate hydrometeor growth processes like aggregation, riming, graupel, anomalous growth patterns of ice hydrometeors. So that is something. Anomalous, why anomalous? Because you will see patterns which you don't expect to see, and from that you can tell what is the wind movement which caused it. You will see anomalous patterns which you would not expect in at a particular altitude. For example, crystals you always expect at the top of a stratiform precipitation, but sometimes you'll see the signatures of crystals at 4 kilometers above ground level. So what is the reason for that? So what are the hydrometeor types and all? This is shown over here. Typical raindrop is 2 millimeter, large raindrop is 5 millimeters, snowflakes, these are the snowflakes. Then you have hail. Hail can be very big. So see, here is a distributed volumetric target. Here is a distributed volumetric target. So, so radar is scanning, as you have already seen, the radar is scanning, and then here is a precipitation. So this is the beam of the radar. This is the beam of the radar. It is possibly making a PPI scan or the plane projection indicator scan. So plane projection indicator scan. So you fix the elevation angle and you scan at various azimuth angles. So here is the range height indicator scan. Here you fix the azimuth angle and you change the elevation angle. You fix the azimuth angle, you change the elevation angle. So this is the difference of the two scanning you have already seen. So let's look at polarimetric variables. Polarimetric variables, which I have already explained. You have the top left corner is the reflectivity values. X-axis is the distance from the radar. So you see here is the location of the radar. Y-axis is the height above the radar. So as Professor Chandra pointed out, you see that this is 60 kilometers while this is 20 kilometers. However, we increase the we rescale the plots just to make sure we see the what the altitude related information properly. Then we have this differential reflectivity at the right. So the values range from -2 to 8 dB. Here the values range from 20 to 60 or mostly 0 to 60. 0 you'll see at the top of the precipitation event. And then you have it's a very heavy precipitation that is taking place. It was during an experiment during Relampago, which was done in Argentina in 2018. So these measurements are from there. So this is the copolar correlation coefficient. As I said, the range of copolar correlation coefficient, it will be 0.8, 0.9 to 1, not less than 0.8 or maybe not less than 0.85. So this is what, see, it's between 0.8, mostly it is between 0.8 and 1. And then you have the radial velocity, So negative values means it's coming towards the particles are coming towards the radar. Positive means they are going away. So this is the convective core, which is the most important part for a or the most interesting part for a convective storm. Okay. So what we did, let's go back once more and see what I have done is I have taken, so measurements are always, it's a range height indicator measurement. It's a range height indicator measurement. So measurements are done like this along. So it's basically scanned at various elevation angle. The azimuth angle is fixed and measurements are done at elevation angle. So what I have done in the next slide is I have picked up one measurement profile along a particular elevation angle and presented. See, here x-axis is the distance, y-axis is the reflectivity. So you see, so for each distance from the radar, there is one value of reflectivity. For each distance of the radar, there is one value of reflectivity. So you are at 35 kilometers, the reflectivity is 36 dBc. Okay, that is reflectivity. Then we come up with what is called spectral reflectivity, that I have been talking about, but I have not presented any results till now. So x-axis is the velocity, the radial velocity, and y-axis is the spectral reflectivity. So what we have done is done a spectral decomposition of the measurements in a radar resolution volume. We have done a spectral decomposition. So what happens is here you at minus 20 meters, so x-axis the velocity. So at minus 20 meters per second, all the particles which have similar velocity, you can see the reflected power corresponding to that. Now, if the particles which are moving at in a resolution volume, if some of the particles are moving at minus 15 meters per second, again radial velocity, that means away or towards the radar along the radar line of sight. It's not perpendicular. If it's perpendicular, you'll see 0 meters per second. Then let's look at differential reflectivity. So here x-axis is the distance from the radar, y-axis is the differential reflectivity. So as I said, look at the values minus 2 to 8 dB, minus 2 to 8 dB, way different. There it was from 20 dBz to 60 dBz. Here it is minus 2 to 6 or 8 dB. So let's look at again another point. See here again 35 kilometers, 3.8 dB. Okay. Now what happens? We'll look at the spectral values. See the spectral values here. Again, you see that the velocity is from minus 25 to minus 10 meters per second, and you have the spectral ZDR. You see that there is some kind of slope. There is some kind of slope to the spectral differential reflectivity values. So now we'll go into how to determine spectral differential reflectivity, how to determine spectral reflectivity. It's not straightforward. Let's look at how it is done. So before that, let's look at how you store the data. We have to look at how the data is stored, because when let's look at let's, huh. So the radar is taking measurements along this angle, elevation angle. Then it is taking measurements along this elevation angle. But scatterers are there all over the place. Scatterers are present all over the place. So what is happening is signal which is being transmitted is returned back to the radar. Then it again, the part which is the signal which is not reflected back goes through. It's reflected from somewhere here, then next, then next. Then what happens for this elevation angle? Again, the radar signal is reflected from scatterers here, then scatterers here, then scatterers here, then scatterers here. Okay, this process goes on and on. So how do you store the data? We have to look at how the data is stored. Data is stored in a data matrix. Okay. So here I have shown. So there is data is stored along. So this is the fast time axis. This is the slow time axis. This is the slow time axis. This is the fast time axis. So slow time axis determines the, well, there is a lot of information present here. Just this small this matrix actually is very complex. If you look, I mean, if you are not used to radar data, it's a very complex matrix. What happens is fast time axis. So this basically represents when the radar signal is going away from the radar and being reflected back towards the radar. As it goes along this and is reflected back and is stored in this column, is stored in this column. Why is it called fast time sampling, fast time axis? Because it is sampled at a very fast rate. It's some megahertz sampling rate. That's why it's called a fast time sampling. It's a fast time. It's the ADC sampling rate, which is called the fast time sampling. ADC is the analog to digital converter. That is what. So it's the ADC sampling rate. And in weather radar, this also determines the sampling rate also is related to the radar resolution volume in weather radars. Then we have to look at the slow time sampling. Slow time sampling is the PRT. What is PRT? Pulse repetition time. So as Professor Chandra already said, you have to send out pulses. and pulses are sent out very fast. Each pulse is sent out every milliseconds. Each pulse is sent out every milliseconds. But milliseconds is still more than microseconds. So the sampling rate is in terms of microseconds. That's why it is fast time. While pulse repetition time is in terms of milliseconds. That's why it is slow time. So this is so as the um, uh, antenna rotates, as the antenna rotates, the signal is stored along this direction for range information and along this direction for pulse information or direction information. So it's pulse information, direction information, all inf uh, included in this matrix. Any questions? This is called the data matrix. It's two-dimensional for this kind of radars. If you have phased array radars, it's a three-dimensional matrix. It's a three-dimensional matrix. If phased array, if you have looked at each receiver will have a matrix like this. Each receiver will have a matrix like this. Any questions? Yes. Huh.
I'm created at different rates. You are storing that and it is processed with a how you are slow time and fast time it is differentiating. That first column for the first angle with the different ranges. Second column for another angle with a different range. So how it is different for the slow time and fast time? When
Okay.
you are sampling analog to digital conversion, when you are sampling the data, you can sample with a high rate. Then your resolution means your dynamic range may get increased, your resolution may get increased. So how that can be different here, the fast time and slow time? I didn't understand.
No. See what you can sample faster. What is the problem again?
I'm not understanding what is slow time,
Slow time is
and fast time.
okay.
How it is.
Slow time is basically slow time. It's called slow time sampling because you are sampling the Doppler information and you are, as I said, it's a very complex matrix, but I'm trying to break it down a little bit. So slow time sampling, you send a pulse. The pulse hits, let's say 10 targets and goes through to, let's say 140 kilometers and returns back. So as many samples you can collect using that radar that is stored along the fast time axis.
But it is depend as what speed I am revolving.
Your speed of rotation,
Number of hits per second.
yeah. The speed of rotation will always be slower than the speed of light.
Yes.
So that's why it's going to be the same, more or less the same angle. Even if you are moving, there is a limitation to how many revolutions you can do per second. Let's say I think you go at like 20 degrees per second max, something of that sort, 10 degrees, 20 degrees per second. Yes. Mhm. Mhm.
Whatever samples we are getting, we need to keep it vertical.
Yes.
In the second PRT, we are seeing at the same location. We don't. It's not good. It is not. We can't change the direction. We have
No. That
no.
is the theoretical assumption while the theory was developed. But you have to, because the antenna is continuously scanning.
True, sir. But the problem is, if you steer the antenna, you can't perform the FFT.
Why?
Because you are seeing at the different direction.
How far? How different? How different?
Suppose if you, for example, first PRT, if you looking at both side, second PRT, if you are going to 10 degrees, then
you cannot go 10 degrees in 1 millisecond. You cannot go 10 degrees in 1 millisecond, isn't it?
No, it's not. It's not like that. My understanding is, I don't know whether I'm correct or not. Suppose we have.
It's more or less the similar angle, maybe slightly off by some millidegrees if you want to say 0.001 degrees or 0.002 degrees, but it's not going to be off by 1 degree or 2 degrees.
No, sir. I don't know. My understanding may not be correct.
Hmm.
As per my understanding, in MST radars and all, the processing is similar, but the way we do is different. Actually, what we do is, for example, if you want to perform a 32-point FFT, we should have a 32 pulse data.
And pointing at the same angle.
Same angle.
Exactly. But that is not is what is happening in weather radar.
Yeah, that's what I'm.
So the idea
But we
is
should
if
point
you can point at the same angle for 32 pulses, it's good. But then you will not be sampling the weather event efficiently.
But sir, if we are not pointing at the same direction, how we will get the data related to that volume?
You are not exactly see if you if you point the radar for one pulse, it is 0.001 seconds. So next pulse it will be off by let's say 0.01 degrees, something like that. Then the next pulse it will be again off by 0.02 degrees, something on of that sort. So you will see the effect of if you take 32 pulses, you will see that the radar antenna would have moved by some degrees. That will happen. You cannot avoid that because it's a scanning
It's a
radar.
mechanical error you are telling.
That's it's not error. It's basically you have to take into consideration the it's called beam smearing. That's the beam smearing effect that comes into the picture when you are rotating the antenna like this.
So in this picture point of view, can you elaborate, sir? We are I got that doubt also.
So what happened here? Huh.
But how many pulses?
Huh. So you see this? You see this? It's not like it's pointing towards. I know MST radar I have never used, but it's a possibility that what you are telling is you have to point it at a particular direction and keep on measuring for 32 pulses or 64 pulses, whichever you want to use.
Yes.
But in this case, it's not so. You are taking measurements continuously as the radar is moving, and you are continuously taking measurement. It's not like you stop, measure for one, so you measure point the radar for 1 degree and for one for 32 pulses you become stationary and then move 32 pulses and then move another move 1 degree, then measure for 32 pulses, move another degree for 32 pulses. No, it's continuously moving. Can you please tell what is the rotation speed of um, um, this S-band radar at CSU?
12 degree per second.
How much?
12 degree per second.
12 degrees per second. Yeah, so it's continuously rotating. It's continuously rotating. Even the radars, I was looking at the specifications of the radar, which are being procured by IITM or IMD. I think it's 6. It should count. It should cover 6 complete 6 revolutions in 6 RPM, something like. Yeah, so it's continuously rotating. As you are measuring, as you are rotating, you are sending. As it is scanning, it is sending out a pulse. Receiving, as it is scanning, it's sending out a pulse. So there is a slight bit of movement as you are taking the measurement, and you are sampling that what you are saying, what you are as you are moving. As you are moving, the return signal you are continuously sampling.
Sir, you just come back to that picture. So, suppose, sir, if you take a 360-degree cone with 1 degree at a time, so 360 points in the x-axis you are
It's
telling.
not 1 degree.
For example, I'm telling.
Yes.
For example, 360 points we are having in the overall cone. 360 points in the x-axis you are telling, and y-axis is
360
PRT.
degrees. Yes.
It's like that.
Yeah. Repeat the question again. It's x-axis is
Suppose
360
we are
degrees.
covering the total azimuth with 360 points, with 1 degree separation.
Yes.
So the slow time axis is 360.
Yes.
Points.
Yes.
This fast time is PRT you are telling. I mean, one pulse.
No. 360 is PRT. Y-axis is the distance information. 360 degrees, 360 degrees information. Again, I'm not saying 360 degrees. Why? Because the 360 degrees information is in the x-axis. Y-axis is the range information.
Okay.
Still not convinced.
Convinced.
No, it's not
Last time
about
I
being
convinced.
you are not able to get it. I'm not nothing to be convinced about. It's that is what is happening. Okay, but what is happening? You are thinking that if you are not pointing at a particular direction, what happens to the radial velocity? That is the problem you have, right? The radial velocity, what you are measuring, will be slightly different. If you point at it for 32 pulses, you measure the radial velocity, and you are scanning like this, it will be slightly different.
So, the FFT technique what you are using, but in the Doppler weather radars, we are going for a pulse pair technique, right?
Yeah.
So their FFT
No,
won't
no,
come.
this is something which I picked
Yeah.
up from the
Right.
internet.
So if they can understand that one, I can the clarity will come to them.
Oh,
In pulse pair also we use number of pulses, I think.
yeah.
Pulse pair also we use sir, in pulse pair also we use but autocorrelation also we have to keep the PRT side by side in PP in that is different. Yeah.
Yeah, that is something which I picked up from the internet. I was because my sequence was changed, so I could not crop that out.
Yeah. Yeah. Correct. 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 Correct.
So I just copied it before lunch, and after lunch I thought, okay, I will crop it. But again, this came up, Anyway, so let's look at the voltage sequence. We have stored the data for each resolution volume, each range bin. So uh, each bin that you see over here, has a IQ value, I and Q value. So uh, so voltage sequence V is equal to I plus JQ. Then you do the autocorrelation. Then you pick up a number of pulses, information corresponding to a number of pulses along the slow time axis. Then you do the autocorrelation. Once you do the autocorrelation, you do fast Fourier transform of this. You get the Doppler power spectrum. Once you get the Doppler power spectrum for one polarization, you do it for the next polarization, H and V polarization. So then what do? You get the spectral differential reflectivity when you divide the two. When you divide the horizontal by the vertical, you get the spectral differential reflectivity. Once you do that, you have all this the autocorrelation and the cross correlation information. You find the spectral correlation coefficient. Okay, so now what happens is, once you have done that, will you get a good result, or will you get the result that I showed in the previous slides for spectral reflectivity, spectral differential reflectivity? No. Why? Why we won't get it? Because we have spectral leakage. When we do the fast Fourier transform or DFT of the autocorrelation function, we have spectral leakage. To reduce spectral leakage, what we have to do is we have to do windowing. When we do windowing, we reduce the spectral leakage. What are the various kinds of window that you could use? You could use Blackman's window, you could use Chebyshev window, you could use Hanning window. Various kinds of windows are there. The similar windows are also used by the signal processors of polarimetric weather radars. So then you have, uh, then what are the ways to that will you will see the difference. You will see the difference when I show the result, how windowing affects the results. It has significant impact. Then we have to do range or time averaging. Many of the when many of the research radars, when they wanted to develop the theory on spectral polarimetry, they were working on time averaging but we didn't have that, where you have to take measurements back to back. You cannot take a lot of time to take measurements and do averaging. That is not possible. So what they did was they used to do time averaging. We have done range averaging. I will explain what is range averaging. Then what is the SNR and spectral? We have to do thresholding. Some amount of thresholding we have to do. So we have to do thresholding based on the SNR of the signal to noise ratio. We have used 5 dB SNR, minimum 5 dB SNR, but that is when the signal is very, we have to find out some information and the signal is very weak. We have to get to use 5 dB. Otherwise, if you have good SNR, you can go up to like 15 dB or something like that. And then you don't want to use spectral you don't want to use data whose spectral correlation coefficient is less than 0.85, because that is some random data. We don't want to use that. So let's look at the results. So here, top left figure is the spectral reflectivity. Here you have the velocity, y-axis is the reflectivity. Then you have the velocity and then spectral differential reflectivity. Here you have the velocity and the copolar correlation coefficient, spectral. See, the look at the data, the without any windowing. This is the data which is presented without any windowing. Now look at the difference. See, this is after we applied a window, just a simple window. The simple window created such a lot of difference. Why this is the, because of the, this could be, what is the, this noisy or data which is varying? It could be because from pulse to pulse, as pulse to pulse, the particle location might change a little bit. Particle might have the orientation of the particle might have changed. Then particles moving a little bit. All of that you see, that impact is you see over this. Uh, you see over here, this and this. But when we do windowing, the whole perspective changes. See? This becomes smoother, this become much smoother. You, and then this is also smoother. Then you have this is the impact of windowing, and you should not see any difference, but this is the impact of windowing. Again, Hanning window, Blackman's window, Chevyshев window. Where do you do so you this is the window where which we have used the autocorrelation function multiplied with the window function. Whatever window function you are trying to use, you could use Chevyshef window, Blackman window, whatever you can use. MATLAB, uh, I will show you the code, and MATLAB has lot of window functions. You can use the inbuilt window functions. You can develop your own window function. Kaiser window, you can try Kaiser window. Then range average. This is what happens when we have windowed signal, which is also range average. See, again, it becomes smoother. What is range average? I will get back. Uh, so here, when we do all this uh, spectral analysis, we do the autocorrelation along this direction and then apply DFT. Then for range averaging, because along this axis is the range information, what we do is we take multiple spectral uh, variables for multiple ranges and average, like take the average along 4 or 5 of these. We might lose a little bit of information, but we smooth out a little bit. But there is a trade-off. You do averaging, you smooth out a little bit, but you are able to see the uh, spectral variation. Instead of seeing the noise, you see the spectral variation or the spectral information. So that is the importance of range averaging. You have to try you cannot just do it and be like, okay, I tried for 6 ranges. No, that is not something you it's not something that you can keep on you can it's written in a book. You have to try and see. If you do windowing for a range averaging for 1 kilometer, that is also not a good idea. Why? Because you are taking information, spectral information corresponding to 1 kilometer, and you are averaging. So that's also not a good idea. So here is the this is the windowed and range averaged data. You can also do time averaging. Time averaging, what you should do is you take divide the matrix which we have seen. So in let's see the matrix again, we'll go back. Ah, so let's say we have the matrix over here. We divide the matrix. So let's say you take 4. Well, 4 is a very bad number, I mean, for this kind of analysis. Let's say 4 columns, and you do find the spectral information along this for 4 voltage sequences. Then you again do it for another 4, then another 4. Then what you do, you do it and then do averaging. Then you do averaging. But they should be close to each other. They should not be very far away. If they are very far away, that also doesn't make sense. Why? Because you are measuring here and you do it after pointing at this, and you do averaging, time averaging. That also doesn't make sense. So you have to make sure that the scene doesn't change, or the weather event doesn't change a lot when you are doing this. So averaging plays a very important role in this kind of analysis. So let's look at what is some uh, measurements that have been done by others. I will show you. So here, Keat and Westbrook, what they did was they pointed a 35 gigahertz radar directly up. They pointed up, and then it was raining along with ice particles present in the cloud. And this is what they saw. So x-axis is the Doppler velocity, is the and y-axis is the height. The wind speed was not that high. The wind speed was not that high. The background wind speed, what I mean. So what you see over here is at 7.5 kilometers, you see something, right? And as it falls, it widens. As you fall, as the particles fall down, or the growth process is happening. As the growth process is happening, you see this thing widens. Here you see, here this region, you see some particles are moving between 0 to 0.5 meters per second. Some particles are moving at 1.5 meters per second. So there is a clear difference in the uh, particle speeds as you move down, so as the growth process is happening, the particles are becoming bigger, some are not becoming bigger. So what you are seeing is the particles which are becoming bigger, you see that the reflectivity information, spectral information, the spectrum information you are getting over here, also the speed information, the speed information as well as the spectral information. So this gives a lot of information over here. See, it's strong over here, and then as you move away, then you have particles which are present over here. It again, it depends on the kind of thresholding they apply. So something which is as low as minus 30 dB, which is pretty low. So you have to be a little careful. Well, they might have thought about it when they did the analysis, but still minus 30 dB is quite low. So they might want to do a averaging a little thresholding more carefully. Sorry, maybe I have never used K band, so I'm just the thing is the result looked beautiful and uh, huh. So this is another precipitation event from the Relampago field experiment. Here you have, again, let's look at x-axis is the distance from the radar, horizontal distance, and then you have the height above the radar as you go up. So this is the reflectivity. This is a stratiform precipitation. The previous one which I had shown, not the last slide, the one maybe 10 slides before that, that was a convective precipitation. Here you see there is a melting layer which is pretty well marked, and then that is again verified by the, if you look at the differential reflectivity, it is blue minus 2 dB, and then here you have copolar correlation coefficient which is close to between 0.85 and 0.9, that is in the melting layer. Why? Because there is a lot of diversity in the particle shape, dimension, melting level, all of that. Because of that you see the it's going close to 0.8. So then here is the distance from the radar and the radial velocity. You see the radial velocity. So uh, let's look at a sheared environment. Let's look at this. So sheared environment. Here is, we'll look at some here. We'll be looking at this place. So here what is happening is wind shear, there is vertical wind shear. So the horizontal wind is different as you move from altitude to altitude. So there is a sheared environment. So the impact is shown over here. So x-axis is the mean horizontal velocity wind, y-axis is the altitude. See, as you see at the top, the mean horizontal velocity is 0. This is an simulation study. So we just wanted to see what is the impact of wind shear on the ice particle trajectory, because as the particles are falling and the dimensions are changing, how the trajectory or the fall trajectory changes. So we wanted to do that. So we looked at the wind shear. So x-axis is the wind shear, wind velocity, mean horizontal velocity. This is the height. So what we did was we took diameter from 1 millimeter, 5 millimeter, and 8 millimeter, and looked at their trajectory. So see, this is the horizontal distance. As at the top, all the three are released. I mean, that's the simulation. All the three are released. But as we go down, this is the d is equal to 1 millimeter. Diameter is equal to 1 millimeter. See, the trajectory is this. As you move, then the 5 millimeter, it is this. 8 millimeter is this. So as it goes down, as the three particles go down, the 1 millimeter particle lands further away, and the 5 millimeters a little less further than the 1 millimeter. Then 8 millimeters is almost below where it was released. Let's look at the spectral polarimetric variables. So before we go, any questions you want to discuss or something? Okay, let's look at the so here there is a pointer over here which points to where the wind shear has been detected. So wind shear in this has been detected using the radial velocity over here. See, see all over as you go along the horizontal axis, you see the mean the velocity over here, or the Doppler velocity, radial velocity, which you see, they are pretty much overlapping on each other, even though the elevation angle is changing. See, there is three elevation angles, measurements along three elevation angles that have been taken. So the three colors correspond to 3.7 degrees, 4 degrees, 4.2 degrees. When you take the velocity information and plot them, you see that they are overlapping on each other at most of the distances. Here what happens, there is a clear difference. So that is the wind shear information. That's the sheared location. So now let's look at, so the altitude range was 2.7 to 3.1 kilometer. Now let's look at the spectral information present over here. So here is the uh, spectral reflectivity, and here is the spectral differential reflectivity. See, the spectral reflectivity, if it is not sheared, what will happen is it will be somewhat Gaussian shape or narrow Gaussian shape. But if it is sheared or turbulent, what you will see is this broadening of the spectral inform or the reflectivity, and then there is a clear trend. You will see a trend. Why? Because all the particles we are moving with different velocity. See, there is a trend over here. There is a trend line. This is we fitted it and found that this is the trend. For the convective storm, we found another place where there was wind shear. Again, there is a trend. So the same analysis was done by uh, University of Oklahoma. Similar analysis was done by University of Oklahoma. So this is the paper from which I have taken it. So here you see the spectral reflectivity information. X-axis is the velocity, y-axis is the spectral reflectivity and or spectral power, and this is the residia. See, for again the reflectivity values or the power values, spectral power values are broad. They are not narrow. They are not Gaussian shaped. They are broad, and then they have a certain trend. They have a trend line, like linear trend. Here the wind shear is a little less than other places. Okay. So then, so uh, Duffernet and Rosenberg, they thought, can we have a generalized kind of values or shape of the spectral reflectivity that can be used? That is the information that is given here. So you see all the figures over here, don't get confused. X-axis is the velocity, that's fixed. Y-axis is the spectral ZDR. Again, it will be ranging from -2 to -6, -7 dB. So here you see, but so let's say there is a case where particles are spheroidal, like this, horizontally oriented. The major axis is horizontally oriented, and then there are particles which are spherical. Two types of particle which are horizontally oriented and spherical, and you mix them up and then leave them in one resolution volume. What will be the shape of the uh, spectral ZDR? You could get any of these depending on the proportion, of mixing. Depending on the proportion of mixing, this is the uh, trend that you will see. But you will mostly see positive values. This is a generalized theory they wanted to apply to everything, all kind of spectral differential reflectivity values. This is a generalized theory they wanted to apply. Then you have spherical and vertically oriented. See, there are all negative values. They are all negative values, but with different shape. But you have to have the negative values. Then you have the just spherical value. You will see that the spectral differential reflectivity oscillates between -1 to 1, -1 to 1. Then Pfizer-Man, they again tried to do the similar thing, but for different perspectives. See, this is the particle types. See, this is the interesting part is, this is the shape of the particles, type of the particles. But then next one is the growth process. So see, the spectral information, they are trying to extract lot of information. The same general trend they are trying to apply to a rhyming process, diffusion growth process, then aggregation. Different trends and all. So now what are the, again, just to there will be ice crystals which are very small. the maximum dimension will be 0.015 to 3 millimeters. If you are not used to these kind of values, this is the dimension of particles we are talking about. The hydrometeors that we are talking about is this. Then you have dendrites which are 0.3 to 4 millimeters. It might vary based on, slightly bit, not a lot. This is what the general literature says. This is the general literature is this range of values. Then you have grapple, slightly bigger. So the growth process is ice crystal. They might grow to aggregates, and then you have grapple, which might grow to hail, and so on. So hail is the biggest. It's really big. You can. There were pictures from Relampago experiment where I saw like grapple were this size. Hail were this big. So the kind of damage they can do, you can imagine. So you have ice crystals, aggregation, rhyming. If it is aggregation, it will be aggregates. If it is rhyming, it is grapple or hail. Dendrites, again, the same process. Depends on the aggregation process and what you get. Yeah, this I think I will stop over here. This is a lot of, it's already 1.5 hours. A lot of things you want to discuss anything. Because already it has been, yeah.
Sir, I have a question.
Huh.
On the basis of reflectivity, you already mentioned shape of the particle. We can find type of the particles. So, is there any process to measure the number density of hydrometer? It's
Yeah.
very important for.
You mean spectral or spectral information or reflectivity, differential reflectivity?
No. Just I want to know: is there any process to measure the number density of hydrometers? Not about the shape. How many number of
Yes.
hydrometer?
Yes. It's there. A lot of literature is there. How many? See, I cannot explain it now because I don't have the material on this. It has been done indirectly using reflectivity, differential reflectivity. It has been done. We can discuss later if you want.
Okay, thank you.
It's not like you are measuring, you are estimating.
Okay.
You have to estimate, yes. Yes. So spectral polarimetry, if you are asking whether spectral polarimetry has been used for determining the number density or distribution, that is something which is still under progress. It's not something which is well established yet. We are also working on the same, some of the things which you saw are published work that we have published, others have published. But the number density is still under progress. That is work under progress. Many groups are working. We are also working on the same thing. Because so the confusion is whether you are talking about spectral or reflect like the polarimetric variables. That is something. Yeah. What else? Yeah, we can do it now. Can I take this? USB. So now what we will do is we will see is so now I will share my screen.
Is it Ubuntu or Windows?
Ubuntu.
Ubuntu. Ubuntu or Ubuntu or
चाहिए क्या ये जूम के लिए क्या ऑनलाइन नहीं जरूर नहीं डायरेक्ट शेयर अच्छा हाँ अच्छा नो 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 ऑडियो शेयर द स्क्रीन और इसको उस तरफ लेके जाना है हाँ एक्सटेंडेड हो गया इसको कॉपी नहीं कर सकते हाँ डिस्प्ले करना है ना डिस्प्ले सेटिंग्स मिरर ओके okay so what I will do is I'll first just run it huh. So so as I was talking about so here see when I am calling this program here we are calculating the autocorrelation here we are calculating the autocorrelation so now let's go step by step so here is the file name of the file name where the IQ data is stored the azimuth angle information is there the elevation angle information is there so all of that is stored in here all the along with the IQ data there are a lot of other information that are stored in this then so the azimuth angle this is again so most of the work I mean I have data corresponding to from Relampago which corresponds to both PPI scan and RHI scan but most of the work which we have done is on RHI scan so that is what I'm going to present so this is a RHI scan information then here is the elevation angle at which the analysis is done so you fix the elevation angle and you do the analysis here is the PRT 1 millisecond then you have the averaged okay here there is no range averaging the range here the work of the averaging is done using this move mean so basically you take six of these spectral spectral information and you average so you take six of these but here there is no spectral averaging or range averaging then once you have once you call this program it will go when you run this code you will go to this it will call this function and the function is compute spectrum z it is present in this one So here you have, once you call the other code, what will happen is the I data will be picked up, Q data will be picked up for horizontal polarization. Then for vertical polarization, the I data and Q data will be picked up. Then the length information will be picked up. Then you have the azimuth information and elevation information. Then you perform, then you this code is called the compute, the function, this compute spectrum underscore z is called. Once you call that, you have it will pick up the information here, the which part of, because the data is stored for a lot of elevation angles, because it data is stored from 0-degree elevation angle to 45-degree elevation angle. So which elevation angles do we need? So that is determined by, and which azimuth angle is needed, that is determined by this and this part of the code, this and this part of the code, which elevation angle and which azimuth angle. Then the combining of the I and Q data. Combining of the I and Q data corresponds to V is equal to I plus JQ, which I presented on the slides. So that is this one. Then you determine the size, and then here is the autocorrelation. We call, well, it's cross correlation, but we do it with itself. So that's why it is autocorrelation. Cross correlation function for MATLAB, but we do it for itself. That's why it's autocorrelation. And then we take the autocorrelation, then we do FFT, then we do FFT shift. If you have used the MATLAB FFT function, you have to use FFT shift. After doing DFT, you have to do the FFT shift. Then you store the data, then here you have the spectrum. You get the spectrum, and then you have the range information and the radar constant, which you have to add over here. You will get the spectral reflectivity. Then we have to go to the next part of the code. The next part of the code is called here. So this is the spectral reflectivity part. Then you have the spectral differential reflectivity and spectral correlation coefficient. Here is, we call the spectral correlation, this part of the code. Compute spectrum underscore z, the spectrum z. So what I have done is, I have made sure that the code which you have to run for range averaging is mentioned over there. You just have to uncomment it. I have commented it, you have to uncomment it. And wherever windowing has to be applied, that also I have commented it, you have to uncomment it. Otherwise it will give the same thing. It will give the same thing again and again. So here is the so all these comments comments are, there are comments written without averaging, without move mean, all and the dates also. I mean, as I work, I continuously updated the code, so I have also mentioned the dates. Distance from the radar, finding the height, finding the velocity. Then let's look at the averaging, the windowing part. Here, see, 55, line number 55, I have mentioned the I have taken into consideration the windowing, hand window, the kind of window which you want. If you want hand window, you take this line number. If you want Chebyshev window, you take this line. So you can uncomment that and start using it. Then we go to the part where we compute the differential reflectivity, spectral differential reflectivity, and spectral correlation coefficient. So here we determine the, so for finding the spectral differential reflectivity, you know, need the spectrum for both H and V. So here is the spectrum for V polarization. Again, if you want the window, you have to use this line number 91. If you don't want the window, you have to use 92. And once you have both, you can, once you have the spectrum for H and V polarization, you can find the uh, correlation coefficient and spectral reflectivity, differential reflectivity. So here is the spectral differential reflectivity, which is calculated over here. So how Subrata, how do we want to operate this? I give you the code and you will circle.
That they can download actually. That's all right.
So whatever you want to try, you can try. Just that you have to read the comments. Without reading the comments, you will just get random values, which will not, and again, if you are using windowing on the H polarization, you have to use windowing on the V polarization. Otherwise, again, you will get random values. So to make sense out of it, you have to use windowing on both polarizations. And this is the this will be called automatically. The moment you run SPV convective, it will be, everything will be called automatically. But for plotting, you will have to run this code pvar hnv strat.m for plotting. So you will have to do that. In case you face difficulty or something when you are plotting this, you can, I'll be here till tomorrow 11 o'clock or so. You can get in touch with me.
So this scope can right. So the thing is that he is giving ready-made code. Hello. Yeah. So he will be giving this code, and there are some uncomment functions like for windowing and other thing. You please try it and try to replicate what he has done. Basically, the idea is that right now you will be getting like those figures, but if you have any access to this I and Q data, then you can plot it for your radar and you can see that how much helpful, because within 1 or 2 days you cannot learn everything. So idea is that try to replicate what he has done, and with those data set it can be, means if you are not using MATLAB, don't worry, because you can convert it into the Python also. This is very much similar, and we are here to help if it is not compiling, and those who have not brought their laptop, they can use those desktops. This is also been connected, but please try to use those codes, okay, because that will be helpful.
Until unless there is a MATLAB code, so if your MATLAB version is very old, that's a different problem. But other than that, I have not directed to any other folder and all the codes will be, that will be shared, you have to save in the save folder, and you start using, you just use this one, spv underscore convective, and then once you are done with that, you just have to run this code directly. It will give you the figures. Once you are done with the part where you don't use windowing, you have to uncomment the windowing parts, and when you uncomment the windowing parts, you will see that the results for the windowed functions will show up.
So we will be sharing those codes and data through some cloud, and we will email you right now. I think Arshad will email, right? Or how we are putting here? You will share the link. Yeah. So he's sharing the link. So in the meantime, I don't know, means we can go for tea and
What time is the
4 o'clock? Tea is ready.
uh,
Tea is ready.
मेरा 1.5 घंटे प्रिपेयर हुई किया हाँ पेन ड्राइव में है radar So once you run this, you can try changing line number 6. So that is line number 6, you will be changing the elevation angle. Then you can I mean, if you want to change the elevation angle, just feed into this and you do the calculation. Anything between 0 to 45. Don't try 60 because 60 data is not there in this file. So you can get up to 0 to 45. Then radar constant you can, so this one will be 60. So this one also you can vary depending on the type of radar you are working on. So you can vary that or you can keep it for now as it is. Then the next step is not here. So to do windowing, what you can do is you can go here. You can start with this line number 55, uncomment line number 55 and comment line number 59. You can start with that. Comment line number 59, uncomment line number 55. It will give you the windowed horizontal spectral reflectivity. Same thing here. You can try that here. 91 and 92.
Hello, everyone. While we're setting up with this sharing of the codes and data files, tea is being served at the reception area. We can join for tea. Thank you so much. We'll assemble back at 4:30.
Going to do scattering, and then scattering is a tough topic to learn after lunch. And in that process, I pushed my friend in front for the topic after lunch, but he was brave. He says, "Bring it on, no problem." Right? So, anyway, I actually enjoyed the discussion between you two. I would rather have it this way than everybody just sits and no discussion. That's too boring. So I'm thankful to you. And okay, I'm trying to watch. What about that person, technical or student in the back? Huh? Okay. Oh, good. You two are back. I was watching. You were missing in the last part of my morning, right? I am telling you, I pay attention to everybody. Good. But I'm happy you are back. I didn't scare you away. Good. Where are you from? TM. Oh, that's somebody else. Oh, you are really from Assam. Oh, then you are in direct competition with Jammu as the farthest place. What about you? Kolkata. Bengali. Yesho, yesho. Good. তোমার নাম কি? Swayam? Sayantar. Sayanton. That's a full name? Samanto. Now you are telling me. Okay. Oh. Short course. Scattering fundamentals 1. So here is the plan for rest of the afternoon so that you don't have to keep guessing when you are going to be set free. You will be set free at 6 o'clock. So I will try to talk faster, and I'm going to allow at least 1 hour for 1 hour for recitation, which means I should be done in half an hour to 45 minutes. I will try. This is a hard topic. Too many vector diagrams and too many equations, but please wear your seatbelt and hang with me, but ask questions, okay? But recitation is mandatory. I was told to tell this. If you need a certificate for today, recitation is mandatory. Mandatory in India, it's called compulsory, right? Yeah. In India, it's not called mandatory, it's compulsory. You understand compulsory. You understand mandatory also. Okay. So, first of all, everybody talks about polarization. Where did polarization come? So, electric field is a vector. Okay? It has a magnitude as well as direction. Okay? Voltage. Is voltage a vector? Some physics student here in the audience. Is current a vector? I will ask this later, but I want you to think. So, and then, but whenever we draw, who's in electrical engineering or physics background? Raise your hand. Only you? There should be more people, yeah. In voltages, have you seen what is called as amplitude phase diagrams? Phase of a voltage. Have you learned about complex phase? It's got an amplitude and phase. It has got a waveform. Good. So many of you are going like this. That's good. So you need to have a phasor. That's called as a phasor. You need to have a combination of a phasor and a vector to have polarization. And so in addition to being a vector, the components of the electric field are phasors. So, and this electric field can lie in one direction because it's a vector. If the direction of the electric field is basically called polarization. If it's vertical polarization. If it's horizontal, it's horizontal polarization. For radar meteorologists, that's enough to understand. But the problem is when you have a radar and it's transmitting in this direction, then with respect to the wave that's going, there is a horizontal polarization and then there is a vertical polarization. You see here? So I'm going to leave it at that. And then we come to what is called a scattering matrix. This morning, I talked about backscattering cross section. You remember? And I said the backscattering cross section, I gave a little formula. It had lambda to the 4 over pi to the 5 k square and then d to the 6 approximately. That's the scattering cross section of a sphere. Whereas if it's a sphere, it has the same scattering cross section and horizontal and vertical polarization. But if it's not a sphere, like the dancing raindrop, then it doesn't have the same scattering cross section in the horizontal and vertical polarization. And he's doing a good job. I was waiting for him to hit one of you with a chair. He's doing very good. You can see I have peripheral vision. I watch everything. And but we need to know the cross section in the horizontal and vertical direction. So instead of scattering as a single component that's connected to the incident electric field and the scattered electric field, when you have two polarization, it becomes a matrix, and that's called scattering matrix. Okay. So that's a 2 by 2. So what happens is you have an incident horizontal and vertical electric field scattered, and that's connected to the incident electric field H and V. And then when you multiply that by the scattering matrix, you get the scattered electric field. So if you want to know more details, the information is available in chapter 4 of the book, right? He agrees. For the sake of this class, I'm not going to go into different alignments. We have to do a little bit of adjustment because while you go to the radar, the wave is going like this. So horizontal is like this, vertical is like this. We have a convention. V cross H is the direction of propagation, the right-hand rule. You all remember this right-hand rule? And then the same wave, when it's coming back and is going back to the, let's say that's the radar, the horizontal is this way, vertical is this way. So the word horizontal has changed direction. So you have to put in a minus sign. So there is an alignment convention, but that's a little bit of detail. So you can get into it if you are becoming so detailed bogged down in this. So so what we can do is we can write the equation in terms of those who have seen dual polarized radars. There are two ports in the antenna. One is for horizontal polarization, one is for vertical polarization. Each port is excited with some amplitude. Ideally, we like to excite them with the same strength of power, so same thing goes out. But in spite of that, sometimes there is a slight difference. This is to account for all this. And when you account for that, you can write down the equation in detail. So the simplest way to think about is you have a horizontal port transmitter, vertical port transmitter that goes to the horizontal port radar, vertical port radar, and then the thing comes back. That's a very simple-minded way to think about it. Okay, now, so when we write E with an arrow on the top of the head, you know what that means? It's a vector. I forgot to ask you, which city you are from? No, not you, him. Where? Nagaland. Hey, you are also competing for very far. You are probably the farthest then, because you have to fly around, right? Oh, now you. So you are like that Assamese. Okay. So that's a vector. So you can see there is a voltage, but that has a hat on it. And so when these things are put together, you have horizontal, vertical, electric field that is incident is proportional to the port that you're feeding them. And then because you know, engineers try to show off they know more math than mathematicians. They write complex equations very quickly. So that's where all these equations come from. So finally, you can write all these equations. That is, everywhere you have two ports going out, two ports coming back, and there is every opportunity to mix it either at the port or at the scatterer level. When you put it all together, you write the dual polarization radar equation. That's the simplest way I can explain in an afternoon when a class that includes first time radar people. I don't want to, what I call, show something that the main job is to show how smart I am and then scare all the new students. So I wanted to explain the concepts in a simple way. So when you do it that way, the voltage equation in the matrix form voltage is lambda over 8 pi Z0, GHGV, EH received EV. So an ideal antenna, which is circular symmetric, will have horizontal gain and vertical gain will be the same. Because if there is any difference, you want to see the difference from the target, not from the antenna. Okay? And these are some error terms. I'm going to skip this. So when we put this together, this is the radar equation. VHVV is lambda over 8 pi Z0, GHGV, and then EHS, EVS. EHS and EVS is the scattered electric field from the target. The scattered electric field from the target at two polarization states It's because it's coming through a two-port antenna. It's coming to the horizontal and vertical port of the antenna. Now I am going to connect this scattered field to the scattering properties of the scatterer at two polarizations. That's coming next. You see here, EHAR received is SHSV, GHGV, and then MHMV are the ports that were eliminated. Let me stop and slow down. I am myself feeling that I am mixing up things. So you have two ports, horizontal and vertical is transmitted. That horizontal and vertical that is transmitted is hitting the scatterer. Scatterer will, let's say the scatterer is very fat in this direction, thin in this direction. It will return lot more power in horizontal direction, in vertical direction. Then that is coming back to the radar, and it is being by the same radar that sees horizontal vertical, and that's fed to the radar. So two ports while transmit, in backscatter two polarizations, and two ports in receive. You understood that? Can you repeat it for me? Mike. Mike for him, please. You first also tell where you are from and then you can repeat it.
It's close by.
Where?
I'm from Mysore, Pune. It's close by.
Mysore, Pune. Well, that's still different from IITM. It's a little farther. Okay, across the street.
Yeah.
If you are successful in crossing all the trucks.
Yes. Yeah.
Okay.
So what I understood is that you have two ports for transmitting, one for each polarization, horizontal and vertical, and then this transmitted beam, which has two polarization, it will be scattered back by whatever is a target. So it's a droplet which has asymmetry, so it is so it will reflect back, and the reflected back signal will again have two polarizations. So to receive them, you again have two ports. So two ports in the receiver, two ports for the transmitter.
Very good. Let's you made ISOR look good by representing. So I am putting everything together here. The received voltage, this is the transmit amplitude, GHGV, that is horizontal gain and vertical gain of the antenna. Ideally, those should be identical, but sometimes there could be a small difference. Same thing, GHGV, because one for transmitting, one for receiving. And then SHSV, this is for the target. This is what we want to know. Okay? And this is for the receiver, MHMV. Okay? So, for an ideal antenna, GH is GV equal to G. So, VHVV, the received voltage, is proportional to lambda G 4 pi r square e to the negative JK20R SH, SV, SHV, SVH, MHMV. This looks like a simple radar cross-section equation for single polarization. If you write one thing at a time, let's make SHV and SVH 0. That is, the target doesn't take cross polarization. It doesn't mix up. It's as if two channels are working independently. It will be a very simple radar. Okay. The propagation?
Yeah, so maybe if you can elaborate that part, like complex number means like imaginary number. So what is the like physical importance of?
Okay. I can actually talk about it if you want some other time. But he wants to know there is a waveform coming. Who's not heard about this imaginary part before? Are there people in this audience? Please feel free to raise your hand. Everybody has heard about it, imaginary part? They're not answering. You've heard. So what happens is when you have, if you go to a physically to a radar, there is nothing imaginary there. There is no ghost. There is a waveform coming and it has a face. What we want to do is we want to grab that face. The only way to grab that face is multiply that with a sinusoid and cosinusoid and then pull out two different parts and then you get the real part and imaginary part. It's called as the complex analytic signal. So it's a real signal to get the face because we want to make the distinction between the signal that rises here like this and goes down or the signal that has already risen and then it starts from here and going down. So we want to know the time difference of the time phase of that phase. Phase in this case is PHASC. So that to account for that, we have introduced this complex notation. You buy that simple explanation? I'm asking you. You agree? IMD. You agree? Okay, thanks. I was going to call your name, but I'm afraid to make another mistake. Was that simple enough? Oh, I know what he is trying to say. In physics, they use the notation e to the j2k0r, whereas in engineering, they use e to the negative j2k0r. That's too much detail for this class at this point. Thank you. Now I get what you are trying to tell me. So let's say you have only one polarization, then the received signal will get only one portion of the scattering matrix. I better speed up because we have a recitation coming. Now that reduces to the power. This equation is same as the radar equation I derived this morning. That is related to lambda square 4 pi. It was 4 pi cube. I will bring 4 pi cube later. Transmitted power g square r to the 4. But you see, because 4 pi times sh is same as sigma, so lambda square g square over 4 pi cube r to the 4, because 4 pi shh square is the radar cross section. So if you peel one polarization separately out, it came back to the simple radar equation. It's a little detailed. Now there is law. This is, I talked, there is, you see here, lambda. Lambda is, what's the formula for that? C over F. F is frequency. So we talked about S, C, X, so many frequencies. The scatterers, in our case, water and ice, they do a lot of things with frequency. Okay? Where is Madhu? Is he here? No. He will be known that he was missing and it is on record. Because for him, we included some computation to up to K band and W band. And then this radar cross section has, you remember the K square that has got dielectric constant. The dielectric constant also creates havoc as you change frequency. And I want to show this part All this stuff, you can find it easily. But now we come to the radar meteorology part of it. A lot of this is engineering. Now, the physics part of that is the radar cross section, in which there is a frequency component of scattering, there is a frequency component of the dielectric constant. These two combinations together make a havoc. Make a havoc means they do lots of changes, but the change can be inverted into information. So let's take the first curve and look at this. This is imaginary part of epsilon r, the relative permittivity, and then the real part. So the complex relative permittivity of water in the microwave range of 2 to 95 gigahertz plotted here. Okay. The solid lines are frequency. So for example, if you want to know S band, you move along this line. That's S band. Okay. And the dotted lines are temperature. So you can pick a temperature. For example, we know at X band, there is a strong variation of attenuation with temperature. So you see at 40 degrees, that's like today in Pune, 40 degrees, right? 40. So you can go, you go from 40 to 30, 30 to 20. The imaginary part keeps increasing. The imaginary part keeps increasing means the attenuation increases as you go to lower temperatures. And the real part contributes to differential propagation phase. So this is one thing you can look at. Then let's go to ice. What do we know about ice? And this is for the experts. Water attenuates a lot, and that's why we couldn't use X-band. What about ice? What's about the attenuation in ice? We all know ice attenuation or in snow is negligible. Whenever I say snow, I have to look at the person from Kashmir. And so you see the imaginary part here is like 10 to the minus 4, 10 to the minus 3, 10 to the minus 2. But the real part is a big number. So here, obviously, at 3 gigahertz, it's very hard to think about. Well, you can see minus 60, minus 50, minus 30. You don't have ice at plus 40 like in the previous figure. But we plot this only up to 0 degree. So this itself influences the backscattering characteristics. Because even in Bombay, where it never snows on the ground, if you go aloft at above the melting layer, there is ice. And in Bombay, I assume the melting layer is around 4.5 to 5 kilometers. Do you do sounding every day? IMD? Where in Colaba? Huh? Near the airport. What at 12Z? 2 times or once? So what's your melting layer? Typically 5 kilometers, 4? Does it even vary between summer and winter? No. Not much.
The data. I have to see the data.
Oh,
Actually,
okay.
I don't remember. Actually,
Anybody else from any northern part of IMD here? You're not with IMD, are you? No. It'll be interesting to see Kolkata. I heard somebody from Kolkata. Any IMD Kolkata? No. Okay. Here is another very interesting example. So you all know that right around the melting layer, below the melting layer is water, above the melting layer is ice. So when this quantity ZE was defined, E stands for what? This is for the not for the people who are learning for the first day. ZE is equivalent reflectivity factor, equivalent to water spheres. But Z is the reflectivity, and there is a 7.2 dB difference when you are in ice region. So you have to pay attention to that. Okay. Now, all these are figures from the book. So if you want to know a lot more details, you can go look at it. This is what data is this?
This is from Italy. Yes, with a province in winter playing for the melting layer was about 1.5 kilometer. Yes. Yeah. Yes.
1.5 kilometers.
Northern Italy. Yes.
Very normal.
Yes, it's typical. Late fall. Yeah.
Where's the Chennai crowd? What's melting layer in Chennai? Do you know? You are all hydrologists. They don't think until the water comes to the ground. Anybody else from South who's meteorologist? Somebody is there from NARL. Huh? It's okay. It still rains. You are asking about, you have MST radar, right? So you should know melting layer. And anyway, Garden Key, it's all fixed 5 kilometers, I think, 4 kilometers. And okay, this is backscattering and absorption. Okay. So we all talk about Rayleigh scattering. This is S band and D is millimeters. 100 millimeters. Wow. Okay. Let's stop at 10 millimeters. So this is Rayleigh region. You can see the scattering is approximately proportional to D to the 6 here. And this is scattering cross section in millimeters. See, yeah.
This figure is a little different from what we are used to seeing for sphere in a this figure which we are this figure which we are seeing here is slightly different from what we are used to seeing in a textbook. I recognize this figure, but in a textbook it will be it goes like horizontal. It still oscillates, but it's horizontal. So
You know why?
no, that's why I asked.
Look at this axis. In textbook, this will be normalized
Ah,
with
okay,
respect to pi a square.
Ah, yeah, yeah.
Good. He's paying attention. Thank you. Because that when it's normalized with respect to pi a square, it won't increase. So this region is optical region. This is me region. And this is Rayleigh region. So what I'm saying is, it's not just about water and then frequency. The dielectric constant also has a mix into the play, which is actually very useful to study the precipitation process, which the people like IITM are very interested in. Okay. This is a very interesting figure. This is what is called as a dense figure. You can sit and stand in front of the figure and speak for 1 hour. There is so much information. This is actually figure 4.6 in the book. So from dark colors to light colors is increase in frequency. Okay. So here also 3 gigahertz that becomes light, it's 95 gigahertz. Do you have anybody here from Madhu's group from IITM who works closely with Madhu? You can tell him I called his name because 95, anything beyond 35 gigahertz in this crowd, only he is interested. So we prepared this graph beyond the regular frequency for him. So in this region, Israeli region, you saw the curve this time? It's flat because it's normalized with respect to pi a square. You see, this is the oscillation that goes into optical region. This is the me region that creates a lot of havoc in radar meteorology. Now, the main thing is you see in the lowest frequency around 3 gigahertz or even C band, which is 5 gigahertz, which is somewhere close. You go like this. This is C band, 1 to 10 millimeters. Okay. This me region takes a huge swing. So it creates a lot of difficulty in interpreting C band radar data. Whereas when you go to X band or higher frequency, that all this jumping up and down settles down. That's another reason why X band radars are very popular. In C band data, you see a lot of resonance, suddenly high ZDR and all that stuff. All that will disappear in X band data. So that's one thing you will see. In fact, we have some dysdrometer computations, right? So that's for tomorrow's recitation. For tomorrow's recitation, we will give you some drop size distributions. You can compute these things yourself for C band, X band, and those types of things. And this is me region. So in S band, the particles never get that high until you get into hail. And there was some group here that lived in a region that gets hail. In the morning, they have changed seats. Where are the hail people? They were sitting in this area this morning. They were from Jaipur? No. You were, you? You are from where? Kolkata doesn't get hail, but if you got to go a little bit away from Kolkata, Kolkata radar will see hail. But actually, I saw some news. Bangladesh gets hail. But Kolkata radar, can you see Bangladesh? Of course, yes. Why am I asking? Can you? Yeah. It's what? 30 kilometers to the border or more? More than that? 50? So long it's below 200 kilometers, I can see. Okay. So this side, you should see hail. I have a feeling we have always had hail, except that people are paying more attention now. Unless people are saying suddenly we are starting to see hail. We were not there before. Anyway, whereas at C band, it's easy to see 4 millimeter particles, which are ice. And you may not see that because Bombay area doesn't have hail. You have hail? No, I mean with your radar, do you see hail? Okay. But X band, all these oscillations will settle down. So overall, X band radars will do very well. Yeah. No, it doesn't have problem. It depends on, it will have a lot of swings in the, you see this, the extreme end is S band. Where the swing is happening, it's around 10 millimeters, 11 millimeters, or 12 millimeters. That's big particle. You don't see such big particles. Before they become that big, they break down. Whereas for C band, it happens around 4 and 5 millimeter particles. 5 millimeter particles could be a melting ice particle. So a melting ice particle will create huge resonance and create large dual polarization signal, which actually can be inverted and can be used as a size estimator for hail size. And you are working with C band data. Now, one momento. And whereas if you go to X band, there is this resonance happens around 3 millimeters, but then there are 4 and 5 millimeter particles that produce a lot more scattering. They will dominate the scattering and squish all these 3 millimeter guys jumping up and down. They'll just squish it down. Yeah, go ahead. This is purely the core frequency. So a solid state or magnetron, it shouldn't make any difference. Yeah. This is very interesting topic, but I don't know if the general audience understands this subtlety. I think all the experts are having fun among themselves. You can be honest with me. Let's see, the ISER guy. Did you get what I'm saying? Or it's a little deep concept. Usko, we need a microphone for him. What? I'm making you nervous? Yeah.
What I understood is that if you're trying to see some big particles like hail or something, if you're using some low frequency radar, it has a lot of oscillations near the me region. That's where the hail particle would probably lie. So it's better to use a high frequency radar.
No, I didn't mean to say that. It's better to use high frequency radar. Depending on what radar you have, you should be able to interpret the observations. But all that I'm trying to say is, first this morning, I made a big swing. Like all the time we were using S-band radar, then C-band radars are more economical, then X-band radars are very cheap. Then what is the subsequent impact? All the impact and subtleties come into looking at ice regions. That's the main message I'm giving. If I have to give you a takeaway message, whereas if you are like the hydrologist, you can wait till the rain comes to the ground. No problem. And then W band I made for the person who is not here. I'm joking. You are in pretty much in the total this region. And then KU is quite good. It's pretty close to X band, but it's in this part of the region. So as you will see, it very interesting. So where this is useful is, which does Bhopal have more than one C band radar? Does it have an X band also? No. Yeah.
We have IMD and S-band, and we have C-band.
IMD is somewhere far away.
Some kilometers.
Yeah.
60 kilometers.
But you don't have, where you have X co-located with C or S, almost. You know, if Chennai, they ever dual polarize that radar, then Chennai may be the only place because within the city. Ah, how far is Andheri to the next closest C X band? 10 kilometers? Yeah.
That is Juhu and Puri, right? And another is Kulava. So one is Kulava southern part as well. One is in Veravali, little bit of higher, and nearby that Andheri airport.
Cool. Okay. So there you'll have an opportunity to look at these little differences.
What you said now, we observe sometimes in Bhopal C-band radar, sometime of suddenly ZDR like 3 dB you observe.
3.
Yeah, 3.
It should go to 7 dB. I have seen 7 dB.
So how to know whether this is due to the me or
it will be in the ice region or lower part of the, like just below the melting layer, where the ice has not melted fully.
Yeah, so that can get like 4 dB.
Now you should be able to see 7 dB sometimes. We have seen 7 dB. If you don't see 7 dB, we need to, that's maybe the physics here. We need to look at it.
No, because if I see 7 dB, I would say that maybe due to the bad calibration.
Yeah, that may be true too. We have to check.
So we have to understand.
Yeah.
So now you said whether this kind of the property can be used to derive like GFR kind of the things and
If you have a second frequency.
yeah. So whether that will be more useful or both should be better?
No, this is used to derive, whereas KUKA, then there used to be S and X before. First of all, I'm very happy because Alan, who is a hydrologist, having a discussion with this figure. Tell me, what's your question or what are you trying to impress your neighbor with? Let's give him the microphone. I'm trying to. He's a hydrologist from Chennai. I have to give him the floor. Here is there. What were you trying to explain?
So I was just asking like how to interpret this graph. We were discussing how to
Oh,
interpret
so
this.
you're asking, not the way you talked, it looked like you were trying to explain to her. Okay, good. How to interpret this kind of graph? It is a little difficult. That's why I'm spending a few minutes. As I told you, in front of this figure, I can spend 1 hour. So size parameter Ka, it's a normalized thing. K is 2 pi over lambda. Lambda is wavelength. Okay. Wavelength for S band is, let's see. Harita, what is the S band wavelength? Harita, somebody answered. Shout out. Do we need lunch? 10 centimeter. Okay. And X band. So you put X band is 3 centimeters, 2 pi over 3 centimeters, and then size of a raindrop, 3 millimeters. Do you have disdrometers in Chennai? You have seen disdrometer data, right? So 3, 4 millimeters. So you just take the ratio that you will get this X axis. Then once you get the X axis, you can read everything. Is that your confusion? Because K0A for hydrologist is a little unusual notation. Mike. Because the reason I'm asking you is other people may be having the same doubt, but they don't want to ask. Yeah.
So, the S band radar mostly looks at the observation in the Rayleigh region.
Yes. Very good. For a hydrologist, that's very good. No, seriously. I don't mean it in a negative way. S band, sorry, what did you say? Me region? Rayleigh
The
region.
Rayleigh
Yes.
region.
S band always works in the Rayleigh region.
That's why we are able to use the Z relationship.
Don't go there. That's too far. That's like saying that's why we are able to commit fraud. No, is it hard because we don't know what else to do? Okay. Yes, if we can use ZR at S band, we can use it at X band also. Doesn't prevent you. No problem. Typically, X band radars will be dual polarized. Hardly anybody will build X band radar without dual polarization. So it will come with the dual polarization parameters. So you are not handicapped to use only ZR. S bands, for historic reasons, those radars are coming with only reflectivity. When you come only with reflectivity, I cannot keep on telling you ZR is no good, but you need something to do rainfall, right? So you have to do that. Are you going to explain more about ZR? Okay. That is, you're going to tell him how bad is ZR? Thank you. They are all hydrologists. I'm trying to convert them to my religion. Okay. I'm going to skip this because I'm eating into the recitation time. I'm going to skip all this. I'm going to skip this. Let's stop right here and transition to recitation, because otherwise there is no end to how long we can keep talking about scattering. Okay, I'm done. We are going to transition to recitation. There are only fewer chairs than the number of people here. How is it going to work? Lottery.
People set up your laptop. Everything is loaded there so they can download it. And you can do all those computational, because now he's also sharing some codes like in Excel. So get that minimum detectable signal, radar equations. I understood what. So like that.
But you need to, they don't let you use your laptop because they are doing live into some YouTube and all that stuff. If they have forced me to not use my laptop, I let
No, cannot use this. Yeah. Cannot use it. That's it.
Well, while he is getting ready, anybody wants to ask general question that comes in the category of ask Chandra anything? Yes.
Uh, when we are using simultaneous transmit, simultaneous receive, linear depolarization ratio possibly cannot be determined, isn't it?
We can. There are procedures to do that. So what you have to do is you have to code the two polarizations,
Oh.
then undo it with the code. You can do it.
So separate coding is there,
Yeah.
phase coding.
Phase coding, yes.
Okay. And same thing
I
goes
have
with
a paper with Nitin
Nit-
to show that.
2008 or
I don't
2007.
remember.
Okay, okay. Now I understand. Okay, fine.
That's a difficult question. Anybody has simple question? From especially the new people. Yes, Iser. Hey, I keep calling you Iser. What's your name?
Weber. Weber.
Huh? Vaibhav.
Yeah.
And
Vaibhav Pacholi.
I can't hear very well. Okay.
Vaibhav Pacholi.
Pachori.
Yeah.
Okay.
I have a very simple question. So the signal that gets scattered in all directions, it might get scattered back into the radar again, right?
Yes.
So how do we take into account that? Is it a signal which is scattered after multiple scattering, received after multiple scatterings, or is it?
So that's a very fundamental question. A lot of the scattering assumptions we are doing here with meteorology is called single scattering. Whereas the same type of scattering studies people do inside material. They shine laser inside not ice crystals, crystals to study. But if you see the scattering centers inside crystal, they are very tight. It will go from one scattering to another scattering, it will come back and then it will come scattering. That's called multiple scattering phenomena. Whereas in weather, we do what is called a single scattering. That's because when it's raining, you can see through rain. You know why? Because the droplets are sparsely distributed. What it means is there is a volume of 1 meter cube. Okay. Even if it is raining 100 millimeters per hour, you can see through the rain, which is very different from if you are in front of a waterfalls or like that you cannot see through, because you take all the raindrop volume and then add up the volume of water and then put it under the whole volume of this volume of space you are seeing. That ratio is even less than 1%. So the volume fraction of water or the scatterers is much less than 1%. Because of that, the probability of multiple scattering strong enough to come back is very, very low. So we do only single scattering. There are some exceptions, but this is way beyond the scope of this class. But we are fundamentally assuming single scattering in studying radars, because that's true 99.99% of the time. That's a very deep, perceptive question. Let's give him a big hand. Other questions? See, sometimes you ask an innocent question that becomes a good question. Anybody else? Yes, please.
So K band. So since it attenuates, um, so if a signal gets attenuated or fully absorbed, basically, so what are you gonna do attenuation correction for when there is no signal? Let's say it got absorbed all, and there is no signal. Is there any signal? I'm not sure.
So if the signal is lost, that's a good point. If the signal is lost completely, there's nothing you can do. So that's why when you build radars at those frequencies, let's say you typically 99% of the time encounter some 15 or 20 dB attenuation for your climatology. That is, you normally encounter 100 millimeters per hour rain. Then what is the typical attenuation you encounter? You compute the statistics for this climate region. You increase the transmit power by so much, so that you will never lose the signal. That's the reason that curves were prepared by the CASA project. And then they said, it's not hopeless. With 15 to 20 dB of attenuation margin, you should be able to see signal. In spite of all this, and also you don't build at these frequencies radars that go up to 100 kilometers, because you build only up they go up to 30, 40 kilometers, because these are small, cheap radars. It's much cheaper to build another radar 40 kilometers away than increase the power of the transmitter by 1,000 times. So that's why the network of radar concept came along.
So I have seen close supercell actually attenuated almost full signal, and there was nothing, and it was very close to radar, but there was no signal after the just immediately after the.
Oh, you have an X-band radar?
Yeah, I have used the data. Yeah,
Really?
I have used. I mean, I have worked with the data. Yeah.
But in which region?
It was US X band.
No, which region the data?
It was in US Southeast.
US?
Southeast.
Oh, southeast of
Yeah.
US, it rains like crazy.
Yeah.
So if you look beyond 30, 40 kilometers, which southeast is what, Alabama? Or?
I don't exactly remember. It was one field campaign where we collected the data in Southeast.
Okay.
Yeah.
So in southeast, it rains like crazy, more than here. Because monsoon rain, the volume of water is high, but the rain rate is not that high. There, the rain rate can get very high in southeast.
Thank you.
Hello. Yeah.
Yes.
So you are suggesting something like we prepare a clutter map similarly, like with the rain rate to prepare some kind of attenuation map.
Yeah, we prepared that to come up with those things. The attenuation statistics.
Okay.
So for different regions, they wanted to see where the number is. It's not 50 dB. So because
for
of
X band.
X band. Well, we prepared that for C band, X band, and
No, because
KU band also.
why I ask, because how about the radome attenuation? Because in X band, it is not like a negligible kind of the things.
Radome attenuation is a problem only when it rains on the radar.
Yeah.
Attenuation is a problem whenever
Yeah,
there
but
is rain.
like for his questions, like he said that I cannot see anything right from the starting. So maybe everything's there. I don't know, means.
The
So I
thing
just
is,
want to
when
know
it's
thoughts.
pouring on the radome,
Yeah.
many times the radome should have some coating. But if it gets pounded with rain too frequently, that coating will go away. Then you will get sheets of water for a brief period. You will get wiped because that's a thick sheet of water.
Yeah.
Thick sheet of water will invalidate my single scattering assumption. So that's like propagating through water. It's like that's why C communications are all at very low frequencies, because we have large antennas. Because water cannot, we cannot communicate with submarine through radio.
Okay.
So that's why.
Yeah. Any other questions for Professor Chandra?
Yes. He doesn't want to let you to go to recitation.
No, this is very interesting, but
Sir, we have seen radar development from Doppler radar to the polarimetric radars, and this industry is expanding. So, what are the next big development that's going to happen in the polarimetric radar? Are there any, or this field is already saturated?
The thing is, I will never say anything is saturated.
No, in terms of technology or new measurements.
I think this is my judgment call. Everybody is jumping on new technology. And that's one thing I will tell. Somehow, after polarimetry, everybody thinks they should go to phased array. That's a huge mistake. Phased array is not new.
Yeah.
Phased array was there in 1980s. I can show you textbooks. It's just that people could not afford phased arrays. Technology had not developed enough. Now, once again, phased array has become accessible because of communication companies. Because of 5G, all these 5G antennas, everybody is putting out phased array antennas because they are made in large numbers. There are many low power phased array radar, which will be used as a network. Radar network, as far as I am concerned, we haven't even scratched 1% of its capability. Just like 15 years ago, you talk to an old person like me, hey, get rid of your landline. That cell phone is going to take over the world. You're not taking my landline away. I'm a doctor and I had to use my special privileges to get landline. You remember old days? You had to be a VIP to get a landline. At that time, many people said, we haven't even seen see what cell phones can do. Now, through cell phone, you can lose your whole bank account in 2 minutes. We had no such privilege before, right? We can make railway reservation and everything. So network of radars, low cost network, this will further morph into combination with electronic scan or other things, and that will change the whole world. And we are still in the very low level of accomplishment. So wait till this radars networks take over, and then there will be a lot of user defined products. The reason I'm saying this is I am already involved in some projects like this that I cannot talk about. One, and this data will change the way AI is going into forecasting. That's where the change will come. Not because of some technology, the user products all will change. This is, mark my words, you can check it after 15 years. Because the data, dense data is coming that until now models didn't even, our current models don't even know how to use them. And that's where the AI is. I'm not like thinking and making some wild speculations. I am myself involved in some projects that I said I cannot talk about. Okay, maybe that's a teaser. You know what a teaser is?
Yeah.
It is you give enough information but don't give too much.
Yeah, so after 15 years, maybe we will coming for felicitating Sachin Deshpande that time retirement. So, okay. So let's thank Professor Chandra.
So now I like
So,
to
yeah.
introduce Renzo Becchini. He is part of our CSU Italian team. Like it started with Luca Baldini long time ago, and then Becchini, Cremonini. Before? Yeah. But he's not here. So he's got one simple thing. Everybody who has a radar and you want to go scratch your head about if my radar is calibrated. So he has prepared a spreadsheet. You can put all your numbers and find out, oh my Lala, I have been doing my reflectivity calculation wrong. So hope you think something like that today. Or people who don't have radars, then adopt a radar nearby and then take all its parameters and go tell those people, your radar is all wrong. So he will tell you how to do that. Renzo, let's welcome him with a big hand. And he has come from Milan or Torino. Which city you like to prefer to use?
Well, I work in Torino. Okay.
For reference, Torino is where they have the Shroud of Christ in a church. Oh, sorry, you need this.
Okay. But meanwhile, if you want to download this file, there is a link in blue, so you can actually download. I will have a few slides of introduction before, and then we can use this file to show some details on the
Renzo, before that,
calibration.
I just want to tell who don't have the laptop, they can come in front of the desktop and they can download this one and they can start playing. Those who don't have laptop, please come to the desktop and internet is available. So you can use those things.
So, okay. So I will start with the presentation. Actually, just a few slides to
Sorry to interrupt. Just make that thing a little bit big. They cannot
bigger.
see from the outside.
Okay. Anyway, I will come again on this. Can I start? Yeah. Okay. So the radar equation. We've been talking about this today already. So in this form is the simplest form that you may find in general. So you have the equivalent reflectivity, zeta E is equal to P0, which is the received power by the radar, R square, R is the range from the radar of the observations. And in the denominator, you have this C, which is the radar constant. Okay, thank you. Yes, okay. This is a radar constant. Sometimes you can find this in the numerator. Well, it depends. And we will see some example of this. Then in detail, this is the radar constant. And what this means, what these terms mean. Basically, you have here, you have the gain of the receiver. You have the TX power, the transmitter power, which is typically of the order of 100, 200 kilowatts for magnetron C-band radars. You have the electric constant of water, and you have C, with speed of light. You have the pulse duration in microseconds, typically can range between 0.5 to 3 microseconds. And then you have the 3 dB antenna beam width in elevation and azimuth. And in the denominator, you have the lambda square and the constant. So everything you have in the numerator, basically, the larger the value, the better the sensitivity of the radar. So if you transmit more power, you have a better sensitivity. If the gain of the antenna is higher, of course, you increase the sensitivity. And a longer duration pulse width also gives a better sensitivity. On the other hand, the wavelength, the larger the wavelength, the lower the sensitivity. That's why high frequency radar is typically higher sensitivity. And very important is this KW. W stands for water. Is typically hard coded in the radar constant. So the reflectivity that comes out from the radar processor is the equivalent reflectivity, which means the reflectivity that is calculated from the received power, assuming that all the scatterer are in the liquid phase. So if we want to compare with the intrinsic reflectivity, for example, for ice studies, this should be taken into account. So in the spreadsheet that you can download, the same radar equation is written in this form. So just okay, we in weather radar we are used to go back and forth between linear unit and log scale very often because typically the reflectivity is expressed in dBz, which is a logarithmic unit. So if you look at this equation and you take the logarithm, 10 times the log, you will have P0 in dB, you will have 20 multiplied by the logarithm of the range minus C. So other times, the constant, like in this case, is in the numerator. So you have the radar constant. So it's like the one before, but you just flip the numerator and denominator, and there are some more details. For example, in this case, the specific path losses are included. LTX, LRX, and LRADOM are the losses in the path between the receiver and the antenna, between the transmitter and the antenna, and this is the loss induced by the radom. So with all these terms, you calculate the radar constant, and then the reflectivity is retrieved from the received power in dBm with this very simple formula. So you have C plus the received power and 20 log of R. So that's the radar constant. And normally we trust that our radar is well calibrated because, the manufacturer sold us a radar and told us that it's well calibrated. So in addition to make all possible electronic measurements of all these components, which can be done, of course, There are other methods we can call end-to-end calibration that allows to check the radar calibration by means of some method. And one of the most relevant methods to determine the radar calibration is by means of a metal sphere. So the principle is that we know the radar cross-section of the metal sphere. So we build a sphere with a given diameter. We lift it up, for example, using a sounding balloon. And then we take measurements with the radar, measure the power, and determine the radar constant. I will show you how we did. And this is something that may be useful to do at least once in a lifetime on a radar, if it's possible, if it's physically possible based on the logistics, because it's very useful actually to assess the real radar calibration. So to do that, we can start from the point target equation, which you've seen this morning. This is the radar equation for a single target, and you see that you have r to the 4 in the denominator, and you have lambda square in the numerator. So this is the main difference respect to the distributed target is that in the distributed target you have r square, and the difference comes from the fact that the distributed target fills the volume, which is proportional to the solid angle. So you have r theta, r phi, and this gives an r square in the numerator. So in the denominator, you end up having r square. So from the point scatter, then we add the radar cross section for the metal sphere, which is a simple area, which is the geometrical area, pi r square. R is the radius of the metal sphere. And then just putting together, replacing sigma with this, we get this point target radar equation for a metal sphere. So from this, we have this point target radar equation, and we assume that G, which is the gain, typically is the gain of the antenna, but in this case, we assume it is the gain of the antenna, which also factors in any other losses, like the path losses between the receiver and the transmitter, and the antenna, and the radon loss. Then we can invert this equation and express the gain, which is this gain here, as a function of Rs, the radius of the sphere, and the ratio of the receive power and the transmit power. So once we measure or know all these terms, then we can calculate the radar constant. So this is a few slides from an experiment that we did with our X-band radar. So we lift this metal sphere with 30, we actually did for 2 different metal sphere to check actually that the results were consistent. We lifted about 200 meter aloft at approximately 1 kilometer from the radar. And we start scanning with the radar across the sphere, both in elevation and in azimuth. And then we looked for several parameters. We first checked the distance. So we checked with the GPS distance, and we checked the range that we get from the radar, because there is also a range 0. There is also a delay in the radar that should take into account all the electronic circuit delay, introduce a delta range at the beginning. So this was checked and matched very well within 20 meters. And then the gain. So the gain actually that we got was around, the maximum was 41.5 dB. This is a histogram for the 2 spheres. And actually, of course, scanning with the radar, we look for the maximum value. The maximum value is where the sphere was actually well aligned with the center of the beam. And from this, with the equation that I've shown before, we calculated the radar constant, which was 78.5 dB. In addition to that, this type of single target with non-RCS allows to calculate also other antenna specifications, like the beam width. So doing this scanning with very fine resolution in the order of 0.1, 0.2 degrees allows to rebuild actually the antenna diagram, at least the main lobe, and check actually the beam width that in this case matched actually perfectly with the nominal beam width of our antenna. And we also did this in 2 dimension, azimuth and elevation, and getting this kind of things. And finally, also the pulse width, also by sampling very accurate, with a very fine resolution in range, it is possible also to check the accuracy of the transmitter pulse. These are all parameters that can be measured with proper electronic equipment, but it's fine also to verify with a completely, procedures which does not involve electronic measurement equipment. Then for every component, for every uncertainty in the radar equation, we have, for example, an uncertainty on the TX power. We have quantization approximations. We have a range accuracy. We sum all, and we got an overall 0.5 dB accuracy on the gain, which reflects on 1 dB accuracy on the radar constant. And finally, we checked with our we checked with actually the radar constants calculated from all the electronic measurements. It was matching within 1 dB, which was a good result. So I have well, this is simply another experiment which led to very similar results. So I think this is not easy in general because it's not so easy to lift a metal sphere well above the surface, because you don't have to have clutter contamination. You need to have a good visibility. We need to add, authorization from air traffic control. But yes, nowadays they do it very often with drones. It is maybe a little bit easier. Although the drone also has its own radar scattering cross section that should be taken into account. The sphere should be sufficiently below the drone to be sure to not interfere with the measurements. So during the same procedure, coming back to the Subatra's questions about radon attenuation, we took a chance that while we were using this metal sphere and it was lifted with a balloon, we also start to wet the radon to see how the gain and the radar calibration in this case would change. So using a sprinkler in an agricultural field, with wet the radon artificially, we try to measure. We have rain gauges and distrometers. Here there is a distrometer. We try to measurements with a lot of uncertainty, the equivalent rain rate of this artificial rain, which was above 100 millimeters per hour. And then while wetting, we did the same procedure, the same experiment. So this is a cartoon summarizing this type of experiment. And so this was while the radon was wet, so we had 41.5 dB gain. I remember this is the gain including the antenna gain, but subtracting all the path losses internal to the radar. So the antenna gain is a bit larger. So let's call it the effective gain. And you see how this gain decreased by up to 7.5 dB during the maximum rain wetting of the radon. And then as soon as switched off the sprinkler, it gradually get back after it dried completely to 41.5. So this is a gain loss of 7.5 dB. So since the gain is calculated twice in the radar equation, because you have the receiving and transmitting, you have G squared in the radar equation. So it actually doubles for a measurement. So that would reflect in 15 dB attenuation due to the wet radon. And this is indeed very realistic values, for at least for our radar, that we have seen during very intense precipitation. This is the sort of maximum limit that we see for our radon attenuation. Of course, during real rain, when you have this 100 millimeters per hour over the radar, it's not only over the radar like with the sprinkler, it will be a few kilometers around the radar. So in addition to the radon attenuation, you also have path attenuation. So what you see, you see the signal going down very even larger than this. Okay. So with that, I think that we can go back to the spreadsheet. And okay, this is very simple. I don't know if you were able to download, and you can actually try replacing some of the constant. So this was for our X-band radar, for example, in this column with the bold fonts, you see all the parameter, for example, lambda square, lambda is 3.2. So yes. Okay, yes. So, this is the resulting value for our X-band radar. But of course, knowing the system parameters for any other radar, you can replace the value. For example, you have lambda, you have the losses, you have the transmitter losses, you have receiving losses, and then you have the TX power, pulse length, beam width, and antenna gain. So you can play with all these values and see how the radar constant would result for any radar. And then we can make a step further and plot the minimum detectable signal as a function of range, given the radar constant. So, for example, just in this case, so we had the 3.2 centimeters for X band. We had losses of about, yes, few, I mean, 0 to 1.7 dB. We did not consider the radon loss. I can actually add 0.6 radon loss. Comma. Yes. 0.6.
Renzo?
Yes.
One question. The equation at the top has two loss radon, but in the other equation you showed radons
Yes,
loss squared.
there was a typo. I don't remember.
At the top, if you can scroll up.
Okay.
Here.
Here. Yes, this is wrong. Actually, because yes, this equation is like the one I shown before is in linear units. So should be L squared because it's the radon loss counted twice. So probably this is from the manual of our manufacturer. So probably it happens with going back and forth from linear to logarithmic. So of course in the logarithmic you will add, if the one-way radon loss is 0.3 dB, the total radon loss is 0.6. But when you do in linear, of course, it's squared. Yes. So we may try, for example, we can replace the wavelength.
Sir?
Yes.
Can you just zoom this?
Okay. It's enough? It's better. Okay, for example, we have 78 dB for our X band. So let's say that I replace, we would imagine to have the same parameter and only change the frequency to C band. How would you expect the radar constant to change? Will it increase, decrease? What do you think? If we replace, C band, we have 5.6 gigahertz. I don't know which frequency you use in India. Is it 5.6 or less? 5.4? 5.4. So we can replace this with 5.4. What would you expect would be the effect on the radar constant? So frequency 565. Okay, 565. So and what will be the radar constant? Sorry? Yes, what would be the radar constant? I mean,
Please raise your hands
no,
if you
no,
believe that
not the exact
is
number.
increasing.
Will it increase this number? This is in dB. Will it increase or will it decrease if we go from X band to C band? It will decrease. Okay, let's try. And lambda, so 5.6. Okay, it will increase because if you look at the equation, actually, so you get the reflectivity from the received power plus the radar constant in this form. So it means that let's start from the suppose you have a volume filled with precipitation with a given reflectivity, and that reflectivity is a property of the rain medium. So that reflectivity will correspond to a given power that you receive from the radar. So if you increase the radar constant, actually it means that the radar that you get is less to get the same reflectivity. And in fact, if you increase the wavelength, going from X band to C band, you are decreasing the sensitivity of the radar because higher frequency, smaller wavelength have higher sensitivity because you have lambda in the denominator in the radar equation. So going to lower frequency will increase the radar constant and decrease the sensitivity of the radar. And it was about 5 dB. Yes. And of course, the effect is quite relevant because lambda is squared. So if you double the lambda, you have a 6 dB increase, or I mean, if you double the lambda, you have a 6 dB decrease in the radar constant, increase in the radar constant. Okay. Okay. Let's go back to the X band and change the pulse width. So the pulse width, maybe I go back one moment to the radar equation. The pulse width is in the numerator and it's to the power of 1. It's only, of course, it is transmitting, so it's not like the gain that is to the power of 2. So what will be the effect in this case if we increase the transmit pulse duration? I think that peak power. H pulse width. Okay, this is a 0.5 microseconds. What about if we go from 0.5 to 1 microseconds? How will the radar constant change in this equation? This is actually easier because it's because there is no square. So doubling the first, let's try to think physically. If we sample in the same medium with 0.5 microseconds, means about 75 meters, right? Resolution. And if we double the duration of the Higgs pulse, it means that this volume of rain will be illuminated with a, double for double period. So it's like transmitted a double of the power. So will we increase or decrease the sensitivity of the radar? The sensitivity, I mean, yes, the sensitivity. And what will be the effect on the radar constant in this case? Any idea? So actually, see, I seen this is a radar constant. Okay, maybe this is confusing. Sorry. This is a radar constant. The formulation I'm using in the spreadsheet. So in this tau, which is a transmit pulse width, is in the denominator. So if I double tau, what will happen to the radar constant? If okay, it will decrease, of course, because it is in the denominator. So, and it will decrease by a factor of 2, which in dB should be 3 dB. Let's see if yes, of course. So it went from 78 to 75 dB. So, and these, well, these are numbers by itself, but we can, so I have the R terminal. I don't know if any of you use R. We use it a lot, but it's very similar to MATLAB, but the only difference is that it's free, so that we don't have to pay. So we can make a quick plot simulation of what is the effect on the radar sensitivity of different radar constants. So we define a range 1 to 100 kilometer, and in this equation, basically, we can how we determine the minimum, the sensitivity of the radar. We need to know the sensitivity of the receiver, and then we can replace in the power, the received power in this equation, the minimum power that our radar can detect. Typically, the minimum detectable signal is around minus 110 dBm. So we can use this value and then plot the reflectivity as a function of range for this power level. Actually, in general, we want to add 2 or 3 dB to the minimum detectable signal to have at least 3 degrees above the noise level to be sure that our measurement is reliable. So we can define PR to be in dB minus 110. And then what we need, and then Z will be, the radar constant. The radar constant, we can try 78, that was our original value. And then the reflectivity, the minimum reflectivity that we can detect will be simply C plus the power and plus 20 log 10 of R. And then we plot as a function of R. Right? And we get this. This is a typical figure of minimum detectable reflectivity. I can add a grid. Cannot see very much. Okay, let's add some. Okay, can you see this? Okay, so in this case, we have this gives the minimum reflectivity that the radar can detect as a function of the range with that radar constant. So we see that at 20 kilometers, we can detect about minus 7 dB. We have 0 dBz at 40 kilometer. And then when we reach 100 kilometer, we have exactly 8 8 dBz will be the minimum level of reflectivity that we can detect. So these are very useful and informative calculation that can be done because it helps a lot also to interpret the data. Because, for example, if you are interested in snow, ice particles, 8 dBz can be already a high value because there will be a lot of snow that you cannot detect with this kind of radar. So, for example, if you are interested in snow, you may decide to use a longer pulse. So, if you use a longer pulse, you can double your sensitivity, which means adding 3 dB basically. So, if we change the radar constant to 75, which is the value that we got with the longer pulse, and we redo the calculation, maybe I can add it as a line. Oh, type this. Ah, no. It's lines, I think. No? Yes. Okay, so you see the red line is the sensitivity with the longer pulse. So it has decreased by 3 dB. So we now are able to detect up to until 5 dBz. So in this case, decreasing, which means, of course, improving the sensitivity of the system. So and so on. So you can actually try this with if you have data from your radars to see what is the effect of the current configuration, and you can also simulate what is the effect of changing some of the parameters that you have the possibility to change, of course. For example, the transmitter power is, I mean, the transmitter pulse width is something that you can change, and many people devise different scanning strategies with different ticks pulse width depending on the precipitation type. So that's so that's it. Any question, curiosity on the radar equation and calibration? Yes. How? Ah, it's very light. It's like I don't know. I don't remember. It's nice. Yes, it's styrofoam. Styrofoam is a solid covered with aluminum foil. It's very light. And yes. And we actually did with the two different spheres because it was the first time that we did when did it this time, and we wanted to check also that the covering of the foil was not altering the results. But with two spheres with different diameter, we got exactly the same result. So you doesn't need to be very precise the covering. It's it's
Hello,
quite
sir. Yeah, this is very informative. Actually, I have one doubt. See, one pulse radar, single pulse radars, that is like klystron, magnetron. This is useful. But in SSPA radars, they are using combination of pulses,
yes.
short pulse and long pulse. In that case, how we are in this equation, how it will be incorporated in that?
Well,
And
actually, you will have two different curves in this example. For example, one until, let's say, 4 or 5 kilometers when you use a short pulse, and another one after that. And then, of course, the two signals in the processor are combined typically to ensure, a smooth transition
yeah, but
between
they
the
are using pulse compression techniques and they
yes,
are getting down sensitivity. Yeah, so pulse compression, how will incorporate in this equation?
the equation.
Pulse compression.
He's saying like we are using like two frequencies. So how to
Two frequencies.
yeah, for solid state radar, like
Yes.
one
Mhm.
short pulse and
Ah,
long
okay.
pulse.
So theoretically, you can put short pulse frequencies,
Yes.
pulse width and other kind of the thing. But practically, then how this sphere calibration he can do?
For the sphere calibration. Okay, I think that yes, Chandra is is an answer.
It's chapter 6. I'm not joking. First of all, you asked a very good question. You see these curves.
Yeah,
maybe
page number 276.
I can show it if you want.
It's in the book.
Yeah.
Oh, you can.
Chapter 6, page
276.
276.
And so go to 278. The radar constant is there.
7, 8.
The radar sensitivity with pulse compression. So it's all there. No worries.
Okay, thank you, sir.
Any other easier question?
No, but one more thing. Show him the curve on page 276. That's very important.
270. Yes, that's the one I
Figure
was.
6.11.
Yes, this one, right?
So what will happen is when you have short pulse, medium pulse, long pulse, the sensitivity can actually jump from one curve to another curve. And you see that how the sensitivity jumps between curves. So that you will see with this combined pulses in solid state radars.
I think they are not incorporating this pulse compression.
Sorry?
They are using pulse compression in signal processing.
Yeah. This is
So,
pulse compression.
yeah.
Along with pulse compression, it will come with pulse compression. It's not just pulse compression. Pulse compression is if you just use one pulse. They will use multiple width pulses to switch things together.
Yeah.
So you see, in this case, the most complex one we built was 3 pulses. Short range pulse, medium range pulse, long range pulse. The sensitivity will jump between 3 sensitivity curves.
So in this case, sphere calibration, if you want to do, in which pulse we can do?
Oh,
It's
it
short.
depends on where the sphere lands in range.
Okay.
So you wait for sphere to move around because you launch the sphere, right?
No, we'll hold balloon with
If you hold, then you move around.
Anyway, it is beyond 10 meters, right? So you will
No,
No, that's
it is in meters, sir. Range. No, it is wrong.
I think it's
I think
kilometer.
it's
It will be kilometer.
Kilometers.
one more typo to the list.
Yes. It is kilometer. Yeah.
So very precisely, I'm asking. So he's saying, like, suppose we cannot launch a balloon like 15 kilometer, and how to see? Suppose we want to do for the short range, medium range, long range. So what should be the appropriate distance he has to go and launch this?
Yeah, I think that logistically, I mean, the distance that is best from a logistic point of view, and maybe then you can do it for one if you cannot do it for all, and then adjust the others based on that.
compression works for one set of pulses. It has to work for the other
Yes,
set of
because I
pulses.
mean, all the
Because
losses.
the most of the
be the
thing you
same.
are calibrating is the unknowns in the antenna, waveguide, and all that stuff. All the digital part is very precise, and you know the waveform. And the thing is, like I used to do sphere a long time ago, but now the modern thing to do sphere is with drones. If you put it at 15 kilometers, you'll be all in clutter. So it'll be a problem.
So do you suggest corner reflector will be the one of the alternative?
Yes, it is. I think Luca did it right on your with the corner reflector, but
Problem with corner reflector is that should be in a fixed place, so you cannot. You have to put in a place that is quite isolated from surrounded because otherwise you get a lot of clutter. So is you can filter the clutter out, but it's not so.
So silent. lot of resources. We put a huge tower just to hold the corner reflector. And we did that. But nowadays you can buy towers and this.
Yeah, we purchased that tetrahedral tower. Means was that.
No. You just then you can bring the tower down. Then when you're ready to do this type of calibration, sphere, corner reflector, and everything, you do once in 2 years or once a year, not regularly, because you shut down the radar and then you declare calibration week. Then actually, Luca and I and others, we've written a handbook how frequently you should do which calibration. This is like which medical test you go for which frequency. It's almost written with that prescription.
Yes, and then there are many other ways to monitor the stability of the calibration. So you do this once, and then you have other very simple methods based on the normal data that you get from the scan, like clutter or other fixed obstacle that you can use to monitor the stability in between this, end-to-end calibration.
Well, this manual can be downloaded from IEEE Explorer. It was published on Radio Science Bulletin December 2015. So just in case you need
Yes, it's a big paper. Yes.
Yeah. So say there, there are any further questions for Dr. Renzo? So if not, let us thanks Dr. Renzo for this session. Now there are few announcements. I think Ms. Shruti will do all those. Please listen to that one.
Okay. Yeah.
नहीं सर इसको व्यू कर दो Thank you, sir, for the interactive session. I would like to make a few announcements now. Mm, Okay. The link for downloading the data and codes from Professor Swaroop Sahu's session is displayed on the screen. He will be available for any discussions today and tomorrow. Thank you, sir. Firstly, now we would like to felicitate two of our lead speakers, Professor V. Chandrasekhar and Professor Swaroop Sahu. I request Dr. Pandithurai to kindly come on the stage. Thank you, sir. I request sir to kindly felicitate Professor Chandrasekhar. Sir. Chandra sir, if you could just stay on this stage. I would now like to request Professor Chandrasekhar to felicitate Professor Swaroop Sahu. Thank you, sir. Mm. With this, we conclude our today's session. The tomorrow's session will begin at 9:30. Participants are further requested to collect their registration kits tomorrow at 9 a.m. Lastly, we would like to invite everyone for the director's dinner at IITM Guest House Lounge at 7:30 p.m. Thank you so much. Okay, please pass the message to everyone who's not here.
Yeah, please. Today we have the director dinner at IITM Guest House. So if some participants has left, please also inform them. We are cordially invited everyone to join us for the director dinner at 7:30 p.m. at IITM Guest House. Thank you. And tomorrow at 9 o'clock, please come to the registration desk and collect your registration kit. Thank you. Have a wonderful evening.